Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to sleep. Tonight, we're drifting into one of the strangest and most quietly unsettling ideas in all of physics. Not a black hole, not the birth of the universe, not even the puzzling fact that one sock can vanish from a perfectly ordinary washing machine and leave no trace behind. Tonight, we're talking about entanglement, the quantum connection that seems to bind things together even when they are separated by enormous distances. It is one of those words that sounds almost gentle at first. Entanglement. It brings to mind threads, ribbons, fishing lines, perhaps a pair of headphones that were placed carefully into a drawer and somehow emerged as a tiny sculpture of chaos. But in physics, entanglement is not just a messy knot. It is something much deeper. It is a relationship between particles so close, so complete, and so peculiar that describing one of them alone no longer quite works. They stop behaving like separate little things with private lives and begin to act like parts of one shared quantum story. And that is where the trouble begins, in the most fascinating way. Because if two particles become entangled and then drift far apart, perhaps one stays in a laboratory on Earth, while the other travels across a beam of light, or across a continent, or in our imagination all the way past the moon and out into the velvet dark. A measurement of one particle appears to be connected with what can be said about the other. Not because a tiny message flies between them like a very determined cosmic pigeon, not because one particle phones the other with the results, and not because the universe has installed an invisible wire between them, although that image is rather tempting. The connection is stranger than that. It is quieter than a signal, deeper than a message, and more difficult to pin down than a cat that has decided the cardboard box is now its permanent legal residence. Before we wander too far into this strange little forest, I would love to know where you're listening from tonight. Are you tucked away somewhere after a long day, with the room dim and the world finally slowing down a little? Are you watching from a city where lights shimmer outside the window, or from somewhere peaceful where the night is mostly wind, trees, and the occasional opinionated fox? And here is a fitting question for tonight. If you could send one tiny particle anywhere in the universe and keep its twin beside you, where would you send it? To another planet, perhaps? To the edge of a distant galaxy? Or maybe just to the kitchen, so it could somehow remind you whether you left the kettle on? Quantum physics cannot quite help with that last one, sadly, but it does have a habit of making ordinary distance feel less ordinary than it did before. If you find this gentle journey soothing, curious, or simply a calm place to let your thoughts loosen before sleep, I would be ever so grateful if you gave the video a like and perhaps subscribed. It helps this quiet corner of science reach other wandering minds who might enjoy a peaceful pause as well. And as always, I do hope the subject is interesting enough to keep you company, but not so interesting that it keeps you awake. Quantum entanglement has been known to disturb the sleep of physicists, philosophers, and anyone who has ever asked one innocent question and accidentally opened the trapdoor beneath reality. But we will take it slowly, no rush, no sharp edges, just a careful walk through the strange place where particles stop behaving like tiny billiard balls and begin behaving more like a shared secret. Now, if you have ever held two gloves, one for the left hand and one for the right, you already know a very ordinary kind of connection. Put one glove in one box and the other glove in another box. Send one box to Paris and one to Tokyo. Later, someone opens the box in Paris and finds the left-hand glove. Instantly, they know the glove in Tokyo must be the right-hand one. Nothing mysterious has happened. No magic has crossed the earth. No secret signal has slipped through the clouds. The gloves had their identities all along. You simply discovered one, and by doing so learned about the other. That sort of connection is sensible, comfortable, and suitable for polite company. Entanglement is not like that. Or rather, it looks a little like that from far away, which is part of why it can be so slippery to explain. The difference is that quantum particles, before they are measured, do not always seem to carry fixed answers in the way gloves do. They are not necessarily hiding a definite left or right, up or down, here or there, waiting patiently for us to peek inside the box. According to quantum theory, some properties remain genuinely undecided until measurement happens. Not undecided because we are ignorant, not undecided because the particle has forgotten to fill out a form, undecided in the physical description itself. The answer is not merely unknown, it is not settled in the way everyday objects settle. This is where ordinary language begins to creak a little, like an old staircase in a quiet house. We're used to things having properties whether or not anyone is looking. A mug on the table is still a mug when your back is turned. Your slippers do not become a cloud of slipper possibilities while you're in another room, at least not unless you have a very mischievous dog. But quantum objects are not everyday objects made smaller. They follow rules that seem alien to us because our brains evolved to deal with apples, rivers, stones, weather, and the social complexity of remembering where we put our keys. We did not evolve to have an intuitive feel for electrons, photons, or the delicate mathematical fog that describes them. So entanglement asks us to be humble. It asks us to admit that the world underneath the familiar world does not have to behave in a familiar way. The table may look solid, the lamp may look still. The quiet room around you may seem like the most normal thing imaginable. But deep inside matter, far beneath the level of touch and sight, nature is keeping a set of rules that feels more like a whisper than a machine. Imagine, just for a moment, two tiny coins created together in a strange quantum mint. These are not ordinary coins. They are not sitting there with heads or tails already chosen. Instead, before anyone looks, each coin is described as a blend of possibilities. Now imagine that the two coins are entangled. When one is finally checked, the other is found to match it in a particular way, even if it is very far away. Again, this is only an analogy, and like all analogies in quantum physics, it is a small candle rather than the sunrise, but it gives us a place to begin. Entanglement is not simply two things matching, it is two things sharing a state so completely that the best description belongs to the pair, not to either particle by itself. That phrase, sharing a state, is important. It may sound mild, almost administrative, as if the particles are co-signing a little quantum document. But the meaning is profound. In ordinary life, we usually describe things individually. This cup is here, that book is there. The cat is on the chair, unless the cat has developed advanced stealth capabilities and is actually behind the curtain. But with entangled particles, the individual description becomes incomplete. The whole contains information that cannot be divided neatly between the parts. The pair is not just particle 1 plus particle 2 in the usual sense. The pair is a single quantum arrangement spread across more than one location. This bothered Albert Einstein very much. He did not like the idea that nature could be so deeply unsettled before measurement, and he especially did not like the suggestion that a measurement here could be connected with an outcome there, without any ordinary signal travelling between them. Einstein valued a universe that made sense in a clear local way. Things should influence other nearby things through causes that move across space at limited speeds. A stone splashes because it hits the pond. A bell rings because something strikes it. Toast burns because someone became overconfident and wandered away at exactly the wrong moment. Cause and effect should not appear to leap across the cosmos in their slippers. Einstein famously complained about what he saw as spooky action at a distance. He was not being dramatic for no reason. The issue cut right into the heart of what reality is supposed to be. Are particles carrying definite hidden instructions all along, like sealed envelopes waiting to be opened? Or does quantum theory reveal something much stranger, that certain properties only become definite in the act of measurement, and that entangled particles are connected in a way no ordinary hidden instruction can explain? For a long time, this sounded like a philosophical argument, the kind that could keep brilliant people politely disagreeing for decades, and it did. But physics has a lovely habit of turning arguments into experiments. Eventually scientists found ways to test whether entangled particles were simply carrying pre-written answers, or whether the quantum connection was genuinely different from anything classical physics allowed. Those tests would become some of the most important experiments in modern science, and they would show that the universe is not merely strange in theory. It is strange in practice, quietly, precisely, repeatedly strange. Still, it is worth being careful here. Entanglement does not mean we can send messages faster than light. This is one of the most common misunderstandings, and it is an understandable one. If two particles seem connected across distance, surely we can use one to tap out a message to the other, perhaps telling someone across the galaxy that dinner is ready, or that they really should have brought a warmer coat. But no, the universe, in its usual elegant and slightly frustrating way, does not allow that. Entanglement creates correlations, not controllable messages. You can measure your particle and see an outcome, but you cannot choose that outcome in the way you would choose words in a letter. The result is not a signal you can command. It is more like opening a window and discovering what the weather has decided to do. This is part of what makes entanglement so subtle. It feels as if it should break the rules, yet somehow it does not break the ones we most expect it to. It challenges our idea of separateness without letting us build a magical cosmic telephone. It makes distance feel less absolute without allowing information to outrun light. It unsettles common sense, but it does not collapse into fantasy. That is often how real science feels at the edge, not like a door thrown open to anything whatsoever, but like a narrow passage into a stranger kind of order. An entanglement is no longer only a puzzle for chalkboards and late-night debates. It has become a working tool. Scientists create entangled photons in laboratories. They use entanglement in quantum communication, quantum computing, and quantum teleportation, which sounds as if someone should be stepping into a glowing booth and arriving in another city with slightly ruffled hair. But the reality is more careful and less likely to cause problems with luggage. Quantum teleportation does not move a person, or even a particle, from one place to another in the science fiction sense. It transfers a quantum state from one system to another, using entanglement and ordinary communication together. The thing being moved is not matter, but information about a quantum condition. Less dramatic than a teleporting spaceship, perhaps, but much more impressive once you understand what is really happening. In recent years, entanglement has even begun to appear in discussions about space, black holes, and the structure of reality itself. Some physicists suspect it may be tied to the deep fabric of space-time. Not just something happening inside the universe, but perhaps something that helps the universe hold itself together at the most basic level. That is a large idea, and we will come to it gently, because ideas that large should not be rushed. Like a good cup of tea, they need time to steep and possibly a biscuit nearby for emotional support. For now, we can begin with a simpler feeling. Entanglement tells us that the universe is not built entirely from isolated little pieces, each minding its own business. At the quantum level, relationships can be just as real as objects. A particle is not always best understood by itself. Sometimes what matters most is how it is connected to something else. That is a strange thought, but also a familiar one in a human way. A note in a song gains meaning from the notes around it. A word in a sentence changes depending on its place. A person, too, is never only a separate point in space. We are shaped by relations, histories, memories, and the quiet pull of other lives. Physics is not poetry, of course, and entangled particles are not little people holding hands across the void. But the idea that connection can be fundamental has a certain resonance to it. The challenge is to understand that resonance without turning it into something it is not. Entanglement is not telepathy. It is not mystical energy. It is not proof that thoughts can change distant objects, or that the universe is secretly a mood board with atoms. It is a precise, testable, mathematical feature of quantum theory. But it is also genuinely astonishing. We do not need to exaggerate it to make it wonderful. The real thing is already enough. In fact, the real thing is far more interesting than the exaggerations, because it forces us to sit quietly with the possibility that reality is neither as separate nor as straightforward as it looks. So tonight, we will take our time. We will begin with the basic strangeness of quantum states, those delicate descriptions of possibility that sit beneath the certainty of ordinary objects. We will look at how two particles can become linked, how their shared state can survive separation, and why measuring one seems to reveal something about the other. We will meet Einstein and his discomfort with the whole business, which is always reassuring because if Einstein found something troubling, the rest of us are allowed to feel a little puzzled too. We will see how John Bell turned a philosophical disagreement into a testable question, and how experiments revealed that the universe does not obey the comforting hidden card trick many people hoped for. Later we will wander into the no-signalling rule, quantum teleportation, future technologies, and the deeper question of whether entanglement is simply one odd feature of quantum physics, or one of the hidden threads from which reality is woven. But there is no need to leap ahead too quickly. The beginning is strange enough. Somewhere in the quantum world, two particles can be described in a way that refuses to separate cleanly into two independent stories. They may travel apart. They may sit in different rooms, different laboratories, different sides of a planet. Yet when we examine them, their outcomes fit together with a coordination that classical common sense cannot fully explain. Not because they are whispering faster than light, not because they carry tiny instruction cards in their pockets, not because the universe is cheating exactly, more because the universe is playing a deeper game than the one our everyday instincts prepared us for. And perhaps that is why entanglement has such a hold on the imagination. It lives at the border between the measurable and the mysterious. It is real enough to power technologies and strange enough to unsettle our picture of the world. It asks us to rethink what it means for things to be separate, what it means to know something, and what kind of reality exists before we look. These are large questions, but they can be approached softly. Science does not always need to arrive like thunder. Sometimes it can enter like evening light, slowly filling the room until familiar shapes look a little different. So settle in. Let the day loosen its grip. Let the ordinary world remain around you, the chair, the blanket, the quiet glow of the screen, while we begin to look beneath it. Beneath the familiar surface of things, beneath the clocks and cups and curtains, beneath all the objects that seem so solid and independent, there is a quantum world where possibility is not merely ignorance, where measurement matters, and where two particles can share a bond so unusual that even the greatest minds of the 20th century had to stop, stare, and wonder whether reality itself was trying to tell us something. And the best way to understand how such a connection can exist is not to begin with distant galaxies or black holes or futuristic computers. It is to begin much smaller, with the strange birth of a shared quantum state, and with the quiet moment when two particles, for reasons both precise and deeply unfamiliar, stop being completely separate things. To see how such a connection begins, it helps to forget for a moment the picture of particles as tiny hard beads flying through empty space. That picture is useful in everyday imagination, and it has served many a school diagram with admirable determination, but it is not really what quantum physics is talking about. An electron is not a little marble with a definite path and a tiny label attached to it. A photon is not quite a miniature glowing tennis ball, no matter how much our brains may appreciate the image. At the quantum level, nature is not best described as a collection of small solid things already carrying every property in a neat little backpack. It is described in terms of states, and a state is the full physical description of what can be known, predicted, and measured about a system. That word state may sound rather plain. It does not arrive wearing a dramatic cloak. It does not announce itself with thunder. In ordinary life, we use it casually. The state of your kitchen may be tidy, questionable, or in need of a small committee. The state of your tea may be hot, lukewarm, or tragically forgotten. But in quantum physics, a state is a very serious thing. It is the description of a system before measurement gives us one particular outcome. It contains the possible answers that could appear when we finally ask the system a question. And this is already a little strange, because in daily experience, we usually assume the answer exists before we ask. The kettle is either on or off. The book is either on the table or not. The cat is either asleep or plotting something behind the curtains. Quantum systems are not so politely settled. Consider a single quantum particle. It might have a property that can be measured in more than one possible way, such as its spin, which is not quite spinning like a top but is often introduced with that word because human language is doing its best. Before measurement, the particle can be in a state that is not simply one definite answer or another. It can be described as a combination of possible results. This does not mean the particle is confused. It does not mean the particle is secretly checking a menu and taking its time. It means that the physical description really includes more than one possible outcome until an interaction, a measurement, forces the issue. Now with one particle, that is strange enough. With two particles, it becomes much stranger. When two quantum systems interact in the right way, their states can become linked. This can happen when they are created together in the same process, when they collide, when they exchange energy, or when they are carefully prepared by scientists in a laboratory. The important point is that the two particles do not merely become similar, they become part of one combined description. Their individual states are no longer complete on their own. The correct description belongs to the pair. Imagine two dancers learning a routine together in a dark room. Before the lights come on, you do not know which exact pose either dancer will be in at the final beat. But if they have rehearsed a paired movement, then discovering one dancer's position tells you something about the other. That is still only an analogy, and a fairly domestic one at that, because real entanglement is not about dancers deciding in advance where to stand. But the helpful part is the shared pattern. The two are not described as independent performers anymore. They are described by the dance they share. In the quantum case, this shared description is not just a convenient shortcut, it is the essential fact. When two particles are entangled, the whole state contains information that does not belong separately to either particle. This is where people often get slightly misled by ordinary examples. We may say that two cards are connected because one is red and one is black, and when you look at one, you know the other. We may say two shoes are connected because one is left and one is right. But those examples are classical. The cards and shoes had their properties all along. Entangled particles are not simply little objects with hidden labels tucked under the carpet. Their joint state can be definite, while the individual outcomes remain indefinite. That sounds odd, because it is odd. It is a little like saying that the relationship is clear while the separate details are not. In everyday thinking, we usually build the whole from the parts. We first describe the parts, then combine them. A sandwich has bread, filling, perhaps far too much mustard if someone has been overconfident, and from those parts we build the sandwich. Quantum entanglement sometimes reverses that habit. The pair can have a well-defined shared property, even when each particle alone does not have a well-defined value for the matching individual property before measurement. The whole is not just a pile of parts. The whole carries something that cannot be cleanly split. This is why entanglement begins at the moment of shared preparation. A common way to create entangled particles is to start with a single system that breaks into two pieces while conserving some property. Conservation is one of nature's great bookkeeping habits. Certain quantities must balance. If a process begins with a total amount of a property, the products must respect that total. Nature may be strange, but it is not sloppy with its accounts. If a particle decays into two particles, or if a photon is converted into a pair of lower energy photons inside a special crystal, the outgoing particles can be bound by a shared requirement. Their individual results may not be fixed in advance, but the relationship between the results is fixed by the way they were born. Think of a quiet laboratory. A beam of light passes into a crystal. Most of the light goes through as if nothing happened, because most of the universe is surprisingly good at ignoring our plans. But every so often, one photon entering the crystal gives rise to a pair of photons leaving it. These two photons may be entangled in properties such as polarization, which describes the direction associated with the light's electric field. Again, we do not need formulas to understand the important part. The two photons have emerged from a shared process, and their measurable properties are now tied together in a way that quantum theory describes as one combined state. They may fly away in different directions, perhaps toward two different detectors. From that moment on, they are not best thought of as two independent little flashes. They're a pair with a shared quantum history. The phrase shared history is useful, but it can also be a bit too soft if we are not careful. Entanglement is not just the memory of having met. Plenty of things share a history without being entangled. You and a friend may both remember the same rainy picnic. Two crumbs may once have belonged to the same biscuit, a tragic but common event. A pair of socks may begin life together in the same drawer, before one embarks on a mysterious independent career. Those are shared histories in the ordinary sense. Entanglement is different because the shared state continues to shape what can be predicted about measurements, even after the particles are separated. It is not emotional, it is not sentimental, it is not a tiny quantum friendship bracelet, it is a precise physical relation. Once the pair has been created, the particles can move apart. One may travel to one side of the room and the other to the opposite side. They may be sent down long optical fibres. They may be separated by kilometres. In principle, nothing in the basic idea requires them to remain close. This is part of what made entanglement so disturbing. We are used to connections becoming weaker with distance. A magnet pulls less strongly when moved away. A whisper fades across a room. The smell of toast, thankfully, diminishes as you walk away from the kitchen, unless the toast is actively burning, in which case it becomes more of a household announcement. But entanglement is not a force stretching through space, getting thinner like an elastic band. It is a structure in the joint quantum description. That does not mean entanglement is easy to preserve. In fact, it is remarkably delicate. Entangled systems are easily disturbed by interactions with their surroundings. This is one of the reasons the quantum world does not usually show itself directly in everyday objects. A particle in a laboratory can be carefully isolated. A photon can travel cleanly through an optical setup. But a warm, noisy, complicated object in the everyday world is constantly bumping into air molecules, exchanging heat, scattering light, and interacting with its environment in countless ways. These interactions tend to spread quantum information into the surroundings and destroy the clean entanglement scientists are trying to study. This process is called decoherence, and although the word sounds like what happens to your thoughts at 3 a.m, it is one of the key reasons the world looks classical to us. Decoherence does not mean quantum physics stops being true. It means the delicate quantum relationships become effectively hidden in the enormous mess of environmental interactions. Imagine trying to hear a single violin note in the middle of a crowded train station during rush hour while someone nearby is eating crisps with unnecessary confidence. The note may still exist, but good luck picking it out. In the same way, fragile quantum relationships can be drowned out by the noise of the world. Laboratories that study entanglement often go to great lengths to isolate systems, cool them, shield them, and protect them from stray interactions. The universe may allow entanglement, but it does not always make it convenient. This is one reason entanglement is not something you can casually use with ordinary objects at human scales. People sometimes hear that everything is quantum underneath, and then wonder whether 2 teacups can become entangled across the room, perhaps explaining why one always seems to vanish when you want it. In the strictest sense, large systems can contain entanglement, and modern physics does study entanglement in complex materials and larger quantum devices. But the clean, controlled entanglement used in classic experiments requires careful preparation and protection. Everyday objects are too hot, too busy, and too entangled with everything around them in a messy way. They're constantly leaking information into the environment. The table, the air, the light, the floor, the cat, and the dust have all joined the conversation, and frankly, they are all speaking at once. A shared quantum state is therefore both powerful and fragile. It gives particles a relationship stronger than ordinary ignorance, but it can be lost through uncontrolled interaction. This balance is important because it helps remove a common misunderstanding. Entanglement is not a magical glue. It is not a permanent invisible thread that cannot be broken. It is a feature of a quantum state, and quantum states can change when systems interact. Measure a particle strongly enough, let it collide with the environment, or allow too much noise into the experiment, and the original entanglement may no longer be available in the form you wanted. In the laboratory, keeping entanglement alive can feel a little like trying to carry a soap bubble across a windy garden. Possible, if you're careful. Humbling, if you're not. So what exactly is being shared? Not a message, not a force, not a little packet of instructions flying back and forth. What is shared is the state itself, the full quantum description of the pair. When physicists say two particles are entangled, they mean the pair cannot be described as if each particle has its own independent state. The complete description is inseparable. That word inseparable is often the heart of the matter. The particles may be far apart in space, but the state describing them does not split neatly into one state over here and another state over there. The mathematical language behind this is very precise, but the verbal idea is simple enough to hold gently. Entanglement means the best description belongs to the relationship. This can be difficult because our imagination keeps trying to smuggle in classical pictures. We imagine the particles agreeing on answers at birth. We imagine them sending secret messages. We imagine them as tiny twins with uncanny coordination. Each picture has a small helpful corner and a large misleading living room. The agreement at birth picture misses the quantum uncertainty. The secret message picture violates the rule that information cannot be sent faster than light. The twin picture makes the particles seem like little personalities with plans, which is charming but not recommended in serious physics, unless the particles have excellent manners. The safer way is to keep returning to the state. The pair is prepared together. The pair is described together. Measurements on the pair show correlations stronger than any ordinary prearranged explanation can produce. Even the word measurement deserves a calm pause. In quantum physics, measurement is not necessarily a person staring dramatically at a machine while wearing a lab coat. Measurement means a physical interaction that extracts information in a definite way. A detector clicks. A photon is absorbed. A particle leaves a trace. The system becomes connected to a larger apparatus, and the vague cloud of possibilities gives way to a particular recorded outcome. Human awareness is not the magic ingredient. The universe does not wait for someone named William to glance over and approve the result. Measurement is about physical interaction, amplification, and record keeping. In a laboratory, the result must be something stable enough to write down, display, or store. Ideally without spilling tea on the notebook. When one member of an entangled pair is measured, the outcome is locally random. That is a crucial point. You do not choose what result you get. If you could choose, you could use entanglement to send messages instantly, and the universe appears very firmly opposed to that sort of shortcut. Instead, each local result looks random, but when the results from both sides are later compared through ordinary communication, the pattern reveals deep correlations. The mystery is not that one side alone produces a surprising message. It does not. The mystery appears in the relationship between the records. Each detector gives outcomes that look individually unpredictable, but together they show order that cannot be explained by simple, hidden, pre-written answers. This is a subtle kind of strangeness, which may be why entanglement took so long to move from philosophical discomfort into experimental triumph. If you look at only one particle, there may be nothing obviously dramatic. No blue sparks, no tiny banner reading spooky behavior detected. The drama is in the comparison. It is in the way the separate results fit together after the fact. In that sense, entanglement is not flashy. It is almost shy. It does not shout across space. It waits until the records are placed side by side, and then quietly reveals that something deeper has been going on. The birth of an entangled state can also happen through interaction between particles that were not originally born together. If two quantum systems meet and influence each other, they can become entangled as a result of that interaction. Afterward, even if they separate, the shared state may remain. This is not unusual in the quantum world. In fact, entanglement is not some rare decorative exception added to physics for dramatic effect. It is a natural consequence of quantum theory. Whenever quantum systems interact and then move apart without losing all trace of that interaction to the environment, entanglement can arise. The universe is not merely capable of entanglement, it seems rather fond of producing it. This matters because entanglement is now seen as one of the central features of quantum physics, not a strange footnote. Early quantum theory already contained the ingredients, but its meaning was not immediately clear. Physicists were busy making sense of atoms, spectra, radiation, and the unexpected behavior of matter. Entanglement emerged from the formalism almost like a quiet consequence that later turned out to be a doorway. At first it was a problem, then it became a test, now it is a resource. That journey from embarrassment to engine is one of the lovelier turns in the history of science. Nature revealed something that seemed too strange to accept, and instead of going away when examined, it became more reliable. One way to make the idea more concrete is to imagine preparing a pair so that a certain combined property is fixed. Suppose the total must balance in a particular way. If one measurement later gives one kind of result, the other must give the matching result needed to preserve the relationship. Again, the ordinary version would be simple. If I break a stick into two pieces and send one piece away, measuring my piece tells me something about the other because the total length was fixed from the beginning. But quantum entanglement is not just a broken stick. The individual outcomes were not merely unknown lengths waiting to be revealed. The pair had a shared state that allowed multiple possible paired outcomes, and measurements selected one outcome while preserving the correlation structure predicted by quantum theory. That last sentence may sound like it has walked in wearing sensible shoes, so let us soften it with an image. Imagine a book that has not yet chosen which sentence will appear on a page until someone opens it, but somehow a second book far away always reveals a sentence related to the first in exactly the right way. Not because the books contain pre-printed pages, not because one book sends a message to the other, because the two books were prepared as one strange joint object, even though they are later read in different places. This analogy also breaks if pushed too far, as most quantum analogies eventually do. Push them gently and they help. Push them hard and they collapse into a small explanatory puddle. But the key idea remains: entanglement is not ordinary matching. It is a shared structure of possibility. In the laboratory, creating that shared structure requires control. Scientists choose systems that can be prepared cleanly and measured reliably. Photons are popular because they travel well and can be detected with precision. Ions can be trapped and manipulated. Superconducting circuits can be engineered to behave quantum mechanically, on chips cooled to extremely low temperatures. Tiny defects in crystals, carefully arranged atoms and other systems can all serve as platforms for entanglement. Each platform has its own personality, which is a polite way of saying each one has its own difficulties. Photons are fast but can be lost. Trapped ions are precise but complex to scale. Superconducting circuits are promising but need cold conditions that would make your freezer look like a tropical holiday. The experimental art is to create entanglement, keep it from decohering, and then measure it well enough to prove it was really there. Because entanglement is delicate, scientists often verify it statistically. They do not rely on one dramatic event. They repeat experiments many times, gathering patterns. This is how quantum physics usually speaks, not through a single particle raising its hand and making a speech, but through repeated outcomes whose probabilities match the theory. The evidence grows through patterns, and those patterns can be extraordinarily precise. This repeated patient style is part of what makes the field so reliable. It is not enough to say something strange happened once. Strange things happen once all the time, especially in kitchens and inboxes. Physics asks whether the strangeness appears again and again under controlled conditions, whether it follows a rule, whether it can be predicted, tested, and used. The shared quantum state also changes how we think about information. In ordinary life, information seems located, the recipe's in the notebook, the message is on the phone. The biscuit is in the tin, unless someone has already conducted an unauthorized experiment. But with entangled systems, some information exists only in the correlations between parts. It is not stored fully in either particle by itself. It appears when the joint system is considered. That is deeply important for quantum technologies, because it means information can be distributed in ways that classical systems cannot copy. This connects entanglement to quantum computing, secure communication, and teleportation of quantum states. But for now, the important point is simpler. Entanglement shows that information in quantum physics does not always live where common sense expects it to live. This is why the phrase shared quantum state is more than a technical description. It is a shift in viewpoint. We are used to treating distance as separation. If something is over there and something else is over here, we assume the full story can be written in two separate notebooks. Quantum entanglement says that, under certain conditions, one notebook will not do, and two independent notebooks will not do either. You need a shared record that describes the pair as one system. The particles may be separated in space, but the description that predicts their joint behavior remains unified. Space separates the locations. Entanglement refuses to let the state be separated in the same simple way. This does not mean space is unreal. It does not mean distance is meaningless. It does not mean everything is instantly influencing everything else in a way we can control. The everyday world is still here and very insistent about it. If you stub your toe, quantum entanglement will not make the table apologize from across the room. Local physics still matters. Signals still have speed limits. Causes still move through the world in orderly ways. But entanglement reveals that the quantum description of reality has a kind of connectedness that does not fit neatly inside the older picture of separate objects with separate properties. The rules are not broken. They are deeper than the rules we first imagined. Perhaps the most useful attitude is not to force entanglement into a familiar box too quickly. It is tempting to say it must be this or that. It must be hidden information. It must be faster than light communication. It must be some kind of physical thread. But the actual phenomenon is more specific and more careful. Two systems interact or are created together. Their properties become described by one combined quantum state. When measured, the outcomes are individually random but jointly correlated in ways stronger than classical explanations allow. Those correlations cannot be used to send messages faster than light, but they do show that nature is not built from fully independent local properties in the way Einstein hoped. That is enough strangeness for one cup of tea. And so the birth of entanglement is not loud. It is not a cinematic explosion of blue light, unless one is making a film and the budget department has become enthusiastic. It may be a photon passing through a crystal. It may be two atoms interacting in a trap. It may be a particle decaying into two products whose properties must remain linked by conservation. A small event carefully prepared, quietly recorded. Yet inside that small event is a profound change. The particles are no longer best understood as isolated individuals. They are a shared quantum system, capable of producing correlations that reach beyond ordinary explanation. This is the first real step toward understanding why entanglement unsettled the founders of quantum theory. It begins innocently enough, with states, interactions, and the natural rules of quantum systems. But once the particles move apart, the shared state raises an uncomfortable question. If the pair is separated, and if measurement outcomes are not simply fixed in advance, What exactly is happening when one result appears and the other is found to match it? Is the world incomplete until measured? Are there hidden details quantum theory has missed? Or does nature really refuse to be divided into separate local facts in the way everyday experience suggests? These were not small worries. They went straight to the foundation of what physicists meant by reality, and they bothered one person in particular, a person who had already changed our understanding of space and time, but was not at all ready to let the universe become quite this strange. The person most famously troubled by all of this was Albert Einstein, which is oddly comforting. If quantum entanglement makes your mind feel as if it has wandered into a room and forgotten why it came in, you are in very good company. Einstein, after all, was not someone who became confused easily. This was the man who had shown that time could stretch, space could bend, and gravity was not quite the force Newton had imagined, but the curvature of space-time itself. He had already asked the universe several difficult questions and received answers that changed physics forever. And yet, when quantum mechanics began suggesting that reality might be uncertain at its roots, and that distant particles might share a connection no ordinary cause could explain, Einstein did not simply nod and say, "Splendid, how delightfully peculiar." He frowned, politely, brilliantly, and with lasting consequences. It is sometimes said that Einstein rejected quantum mechanics, but that is not quite fair. He helped create it. Long before he became the grand critic of quantum strangeness, Einstein had made one of the great early contributions to quantum theory by explaining the photoelectric effect, where light striking a metal surface can release electrons. This work helped show that light behaves as if it comes in packets of energy, what we now call photons. So Einstein was not an outsider grumbling at a new theory he did not understand. He was one of the people who helped open the door. The difficulty was that once the door was open, quantum theory led into a house with very unusual furniture. By the 1920s and 1930s, quantum mechanics had become astonishingly successful. It explained the structure of atoms, the behavior of light and matter, and the strange patterns seen in experiments that classical physics could not handle. It was not a vague speculation. It worked beautifully, too beautifully to ignore. Yet the way it worked seemed to ask physicists to give up something many of them had assumed must be true. It asked them to accept that certain properties of a particle might not have definite values before measurement. It asked them to accept that the theory could predict probabilities with incredible accuracy, while not always describing a clear hidden reality underneath those probabilities. And for Einstein, that was a serious problem. Einstein wanted physics to describe a world that exists clearly and independently of observation. A particle should have properties whether or not anyone measures them. The moon should still be there when no one looks at it. A teapot should not become a fog of possible teapots just because you have stepped out of the kitchen. This may sound obvious, and in daily life it usually is. If your keys are not on the table when you look, you assume they were somewhere else before you looked. Not that they waited in a shimmering cloud of key potential until your eyes selected a location. Einstein believed that a good physical theory should describe that underlying reality, not merely tell us the odds of what we will see when we check. This concern is often summed up in the phrase, "God does not play dice," though like many famous remarks, it has been polished by repetition until it sounds almost more like a slogan than a serious philosophical position. Einstein was not simply objecting to randomness, because he personally preferred tidy universes, although one suspects he did appreciate a certain elegance. His worry was deeper. If quantum mechanics only gives probabilities, is that because nature itself is truly indeterminate, or because the theory is incomplete? Perhaps there are hidden details we have not yet discovered. Perhaps particles really do carry definite properties, but quantum mechanics does not tell us what they are. Perhaps the dice only seem to be rolling because we cannot see the mechanism inside the table. This is where entanglement became such a powerful tool in the argument. Einstein realized that the problem was not just about randomness. It was about locality, the principle that objects are only directly influenced by their immediate surroundings, and that effects cannot leap instantly across space. Locality fits beautifully with relativity, Einstein's own great achievement. In relativity, nothing can send information faster than light. Causes do not instantly jump from one side of the universe to the other like impatient fleas. They move through space-time with a limit. This speed limit keeps the order of cause and effect from falling into chaos. It prevents the universe from becoming a place where tomorrow can accidentally knock over yesterday's vase. So when quantum mechanics seem to imply that measuring one particle could be tied to the state of another faraway particle, Einstein saw trouble. Not small trouble either. This was the kind of trouble that sits quietly in the corner during dinner and slowly rearranges the furniture of reality. If the particles are separated, how can one measurement be connected with the other instantly? If nothing can travel faster than light, then either something about quantum mechanics is incomplete, or our understanding of locality needs to be changed. Einstein preferred the first option. He suspected that quantum mechanics, for all its success, was not the final story. In 1935, Einstein joined with Boris Podolsky and Nathan Rosen to write a famous paper that sharpened this concern into a precise challenge. It became known by the initials of their surnames, though in a sleepy narration it is perhaps kinder to simply call it the Einstein-Podolsky-Rosen argument. Their goal was not to prove that quantum mechanics gave wrong predictions. The predictions were excellent. Instead, they wanted to show that quantum mechanics could not be a complete description of physical reality. That word complete mattered enormously. A complete theory, in their view, should account for every element of reality. If something can be predicted with certainty without disturbing a system, then there should be some corresponding fact about the system that the theory describes. Quantum mechanics, they argued, failed to describe such facts in entangled situations. The original argument used properties like position and momentum, which can become mathematically involved rather quickly, and mathematics at bedtime can be a risky business, unless one has brought a warm blanket and a very patient pencil. The easier modern version uses paired particles with properties like spin. Again, spin is not quite ordinary spinning. It is a quantum property that can be measured in different directions, but we do not need the technical machinery to grasp Einstein's discomfort. Imagine two particles prepared together so that their results will be linked. They then travel far apart. If you measure one particle and obtain a result, quantum theory lets you predict the corresponding result for the other particle with certainty, provided the same kind of measurement is made there. But if the distant particle was not disturbed by your local measurement, because it's far away and no signal had time to reach it, then perhaps that distant particle must have had its result already. If so, quantum mechanics should have included that definite value from the start. Since it did not, the theory must be incomplete. That was the heart of the challenge. Einstein and his colleagues were not saying, look, quantum mechanics is useless. They were saying, look, quantum mechanics cannot be the whole story if it leaves out real properties that must already exist. It was a careful argument built around the idea that reality should be local and definite. Local meaning no instant influence across distance. Definite meaning physical properties exist whether or not we measure them. Together, these assumptions felt natural, even necessary. They still feel natural to most of us, because they match the way tables, lamps, clocks, and badly behaved printers appear to work. The famous phrase spooky action at a distance came from Einstein's discomfort with the idea that quantum theory might require some kind of non-local connection. He did not mean ghosts, of course. He meant that the connection seemed unacceptable as a foundation for physics. To him, a theory that allowed distant measurements to be linked without a clear local mechanism seemed to abandon the kind of reality science was meant to describe. It was not enough for a theory to predict what instruments would say. He wanted to know what was really there. Across from Einstein, in both debate and temperament, stood Niels Bohr, one of the central architects of quantum mechanics. Bohr did not think quantum mechanics was incomplete in the way Einstein claimed. He believed Einstein was trying to demand from nature a kind of classical clarity that quantum phenomena simply do not provide. Bohr's view was subtle, and sometimes expressed in language so dense it could make even a determined reader feel they were walking through fog while carrying a wardrobe. But the broad idea was that the meaning of a quantum property depends on the experimental arrangement used to measure it. You cannot always speak of a particle having a definite value independent of the measurement context. The act of measurement is not merely revealing a pre-existing fact in the classical sense. It is part of the conditions under which that fact becomes meaningful. This disagreement between Einstein and Bohr was not a small technical quarrel. It was a disagreement about what physics is for. Is physics meant to reveal a clear underlying reality, with objects carrying definite properties and causes moving locally through space? Or is physics about the outcomes of experiments, the structure of observations, and the limits of what can meaningfully be said? Einstein wanted the deeper picture. Bohr insisted that quantum theory was telling us the deeper picture may not look like the old one. If that sounds more like philosophy than physics, that is because at the foundations the two sometimes meet for tea and refuse to say who invited whom. The debates between Einstein and Bohr are often presented as if Bohr won and Einstein lost. That is too simple. Bohr defended the working structure of quantum mechanics, and history has certainly favoured the theory's predictions. But Einstein's objections were not useless resistance. They were productive discomfort. He kept pressing on the weak points, asking whether the theory was complete, whether reality was local, whether measurement could really play such a strange role. His refusal to be satisfied forced the questions to become sharper. In science, a good objection can be a gift, even when the objector does not get the answer they hoped for. Einstein's worry helped turn entanglement from a strange mathematical feature into a central question about the nature of reality. For many years, though, the discussion remained mostly philosophical. Quantum mechanics worked. The calculations matched experiments. Engineers and physicists could use it. Atoms behaved as predicted. Lasers, transistors, and eventually much of modern technology depended on quantum principles. So one might be forgiven for thinking, if it works, why worry about what it means? This is the practical attitude, and it has much to recommend it, especially if one has a deadline. But foundational questions have a way of waiting patiently. They sit at the edge of the theory, quiet as a cat beside a closed door, until someone finally asks what they have been staring at. Einstein's challenge can be made clearer with a simple everyday comparison. Suppose two envelopes are prepared in a room. One contains a red card and one contains a blue card. The envelopes are sealed and sent to opposite sides of the world. When you open yours and find red, you instantly know the other contains blue. There is no mystery. The colours were fixed when the envelopes were prepared. Your discovery did not change the distant envelope. It only revealed what was already true. Einstein suspected entangled particles might work in some deeper version of this way. Perhaps quantum mechanics did not tell us which card was in which envelope, but perhaps the answer was still fixed by hidden variables, hidden features not included in the theory. The quantum view is more unsettling, or it says the particles are not simply like envelopes with pre-written cards. Before measurement, the pair is described by a shared state containing possible outcomes. The individual result is not merely unknown, it is not definite in the same classical sense. When measurements are performed, the outcomes appear random locally, yet correlated together. Einstein thought that could not be the final account. The distant particle, he argued, cannot have its reality created or altered by something done far away, not if relativity is right. So the missing detail must be in the theory. Somewhere beneath quantum mechanics, he believed, there should be a more complete description restoring local reality. It is important to notice how reasonable this sounds. Einstein was not being stubborn in a foolish way. If someone told you that opening an envelope in London somehow helped determine what card appears in an envelope in New Zealand, and that no message passed between them, you would quite sensibly ask whether the cards had simply been placed there earlier. That is not an irrational response. It is exactly the response common sense recommends. The astonishing thing is not that Einstein objected. The astonishing thing is that later experiments would show that common sense in this case does not survive intact. But at the time, there was no clear experimental way to settle it. The Einstein-Podolsky-Rosen argument seemed to many people like an interpretation issue. Quantum mechanics gave predictions. Hidden variable theories might give the same predictions if cleverly constructed. Perhaps choosing between them was a matter of taste, like preferring tea strong or mild, except with slightly more implications for the structure of the universe. For decades, many physicists focused on using quantum mechanics rather than worrying about its philosophical meaning. The practical successes were too great to ignore, and the foundational puzzle seemed too slippery to test. Einstein himself continued to believe that quantum mechanics was incomplete. He did not produce a successful replacement, but he held firmly to the idea that a deeper theory should exist. In that deeper theory, reality would be definite and local. Particles would have properties, measurements would reveal them. Distant events would not instantly influence one another. The universe would preserve the kind of clarity he felt physics required. It would still be subtle, of course. Einstein was not asking for simplicity in the childish sense. Relativity itself is subtle enough to make a clock sweat. But he wanted a reality that did not depend on observation in the peculiar way quantum mechanics seem to suggest. There is something almost human in this scientific discomfort. Einstein had already taught the world that common sense could be wrong about time and space. He had shown that simultaneity is not absolute, that moving clocks run differently, and that gravity changes geometry. He was not afraid of strange ideas, but he wanted strangeness with structure. Relativity, for all its surprises, has a clean and majestic order. Quantum mechanics seemed different. It worked, yes, but it seemed to replace clear physical description with probabilities and measurement rules. To Einstein, that felt like a sign that something deeper was missing. The universe, he believed, should not be reduced to a set of betting odds, however accurate. Bohr and many others accepted the probabilistic nature of quantum mechanics more readily, though not always comfortably. They argued that the demand for hidden definite properties may be an old habit carried over from classical physics. Perhaps asking what value a particle had before measurement is sometimes like asking what song a piano note was playing before anyone pressed the key. The question assumes a context that does not exist. For Einstein, this sort of answer was not enough. He wanted the note to have a reality independent of the performance. Bohr might say the phenomenon includes the instrument, the arrangement, and the act of measurement. And there they stood, not merely disagreeing about particles, but about the grammar of reality. The word reality itself became slippery. Einstein, Podolsky, and Rosen tried to define an element of reality in a practical way. If you can predict something with certainty without disturbing it, then that something corresponds to reality. Bohr responded that the phrase without disturbing it did not fully capture the quantum situation, because the entire experimental arrangement matters for what can be meaningfully predicted. This reply frustrated many readers, then and now, because it does not feel as crisp as Einstein's demand. But Bohr was pointing to something deeply quantum. Measurement choices do not merely uncover classical facts, they help define which facts can appear. From our sleepy vantage point nearly a century later, we can see that both sides were circling a genuinely profound issue. Einstein was right that entanglement exposes a tension between quantum mechanics and classical ideas of locality and definite properties. Bohr was right that quantum mechanics cannot simply be forced back into classical language without losing what makes it work. The unresolved question was whether Einstein's preferred deeper explanation could be tested. Could one distinguish a universe where particles carry hidden instructions from a universe where entanglement is genuinely non-classical? Could the argument move from philosophy into experiment? That question matters because science advances most powerfully when vague discomfort becomes measurable. It is one thing to say, This theory feels incomplete. It is another to find a test that nature can answer. For a long while, no one knew how to do that. The hidden variable idea seemed flexible enough to hide behind the same predictions quantum mechanics made. If every experiment came out the same either way, then the debate might remain an elegant but unresolvable quarrel. A kind of intellectual chess match played in the quiet rooms of theoretical physics, while the particles themselves refused to comment. Einstein did not live to see the full experimental turn, but his worry did not vanish. It lingered in the foundations of physics, waiting for the right person to translate it into a sharper question. The strange thing is that Einstein's attempt to show quantum mechanics was incomplete ended up revealing just how radical quantum mechanics really is. By insisting that the theory must be tested against local realism, he helped set the stage for a result that would be far more surprising than many expected. The universe would not simply say yes to Einstein or yes to Bohr in ordinary language. It would answer through correlations, through statistics, through measurements repeated again and again on entangled pairs, and the answer would be quiet, precise, and deeply unsettling. Before that answer arrived, though, one had to turn Einstein's philosophical worry into something an experiment could actually check. It was not enough to ask whether particles have hidden properties. One needed a way to show what any local hidden property theory must predict, and then compare those predictions with quantum mechanics. That required a new kind of thinking, a bridge between deep philosophical assumptions and laboratory results. It required someone to take the question of hidden cards in sealed envelopes and ask, with extraordinary clarity, what patterns should appear if the cards were truly written in advance. The person who finally found a way to turn that question into something nature could answer was John Bell, a physicist from Northern Ireland with a gift for seeing through fog. Bell was not trying to make quantum mechanics sound mystical. He was not trying to decorate the universe with mystery for mystery's sake. He was asking a very careful question. If Einstein was right, and if particles really do carry hidden instructions that determine their measurement results in advance, then what kind of patterns should we see when we test many entangled pairs? And if quantum mechanics is right, what patterns should we see instead? That may sound modest at first, almost like a bookkeeping exercise, but it was one of the most important shifts in modern physics. Before Bell, the argument about entanglement could seem like a disagreement about taste. One person might prefer to say particles have definite properties underneath the quantum description. Another might prefer to say quantum theory is complete as it stands. Both could point to the same experiments and say, look, my interpretation still survives. It was a little like two people looking at the same sleeping cat and disagreeing about whether it is dreaming of fish or plotting against the sofa. Interesting perhaps, but hard to settle unless the cat chooses to testify. Bell changed that. He showed that the difference between Einstein's preferred kind of explanation and quantum mechanics was not merely philosophical. It could show up in the statistics, not in one single measurement, not in a dramatic sparkle from one particle. But in the long run, after many pairs had been prepared, separated, measured and compared, the universe would reveal whether hidden local instructions could really account for the results. To understand why this mattered, let us return to the hidden cards idea, because it is friendly enough to sit beside us while the stranger ideas stretch their legs. Imagine two cards placed into two sealed envelopes. One envelope goes to Alice, the other to Bob. Alice and Bob are far apart, perhaps in different cities, perhaps on different mountains, perhaps in two laboratories separated by enough distance to make the tea arrive cold. Each time they receive a pair of envelopes, they choose a question to ask their card. In an ordinary hidden card world, the answers are already printed inside. Whatever Alice asks, her envelope contains the response. Whatever Bob asks, his envelope contains the response. The cards may have been prepared in a coordinated way, but once the envelopes leave the source, nothing Alice does can change Bob's card. The results are local and prearranged. This is the sort of world Einstein hoped might exist underneath quantum mechanics. The quantum state in that view might be incomplete. It might fail to reveal the hidden list of answers carried by each particle. If we only knew those hidden instructions, the randomness would disappear. The particles would be like sealed envelopes all along. We would not have spooky action at a distance, just ordinary ignorance. When Alice opens her envelope, she learns something about Bob's, but she does not affect it. Sensible, comfortable, very suitable for anyone who likes their universe with a firm chair and a clear timetable. Bell asked what such a hidden instruction world would imply. Suppose each particle carries a complete set of answers for any measurement Alice or Bob might choose. Not just the measurement they actually perform, but the measurements they could have performed. This is important. In a local hidden variable theory, Bob's particle cannot know what Alice decides to measure far away at the last moment, and Alice's particle cannot know Bob's choice either. So if the particles are going to produce the right correlations without communicating, they must carry enough instructions from the start to answer whatever question comes their way. A little like a very well-prepared student walking into an exam with answers to every possible question, which, for the sake of academic honesty, we will imagine as a purely theoretical situation. Now, if those hidden instructions exist, there are limits on how strongly Alice's and Bob's results can be correlated when they choose different measurement settings. That is the key. Bell found that local hidden card theories cannot produce just any pattern. They are constrained. They can produce correlations, certainly. Ordinary prearranged systems do that all the time. If one envelope contains a left glove and the other contains a right glove, the results are perfectly anti-correlated when both people ask the glove question. If one box contains a red marble and the other a blue marble, opening one tells you about the other. No mystery. But when Alice and Bob are allowed to choose among several different ways of measuring, local hidden instructions can only coordinate the results up to a certain limit. Quantum mechanics predicts that entangled particles can pass beyond that limit. That is Bell's great insight in plain language. If the world is local, and the outcomes are determined by hidden properties carried from the start, the patterns must obey a certain boundary. If quantum mechanics is right, the patterns can cross that boundary, not by sending messages, not by allowing Alice to control Bob's results, but by producing correlations that are too strong, too delicately arranged, to be explained by ordinary local pre-written answers. This is the point where the mind may want to wander off and make a sandwich, because the claim sounds subtle. It is subtle, but subtle does not mean vague. Bell's theorem is precise. It says that no theory built from both locality and pre-existing hidden answers can reproduce all the predictions of quantum mechanics. Put even more gently, if entangled particles really behave as quantum theory says they do, then the universe cannot be explained as a collection of little objects carrying private instruction cards that simply wait to be read. Let us give the hidden cards a slightly richer life. Imagine Alice and Bob are each given a box with a small lamp on it. Each box has several buttons. When Alice presses one button, her lamp flashes either warm or cool. When Bob presses one of his buttons, his lamp also flashes warm or cool. The boxes have been prepared together, then separated. Alice and Bob choose which buttons to press only after the boxes are far apart. Later they meet, compare notes, and look for patterns. If the boxes are ordinary machines with pre-written instructions inside, then each box must contain a plan. If Alice presses the first button, flash warm. If she presses the second button, flash cool. If she presses the third button, flash warm. Bob's box has its own plan too, coordinated with Alice's from the beginning. The plans can be clever, very clever. They can be chosen at random from a huge list at the source. The source can prepare boxes with different hidden strategies each time. The strategies can be arranged to mimic many quantum patterns. But if the boxes cannot communicate after separation, and if each outcome is determined by a plan already inside the box, then there are statistical limits. Over many trials, the correlations between Alice's and Bob's flashes cannot exceed a certain strength. Bell found a way to identify that limit. Quantum entanglement predicts that the lamps, if they were quantum lamps rather than sensible household lamps, available from a shop with questionable assembly instructions, would beat the limit. Not all the time in every single trial, because individual outcomes remain random. But in the overall pattern, after many repetitions, the results would fit together too well for hidden local plans. The universe would behave as if the boxes were coordinated in a way that cannot be reduced to pre-written instruction sheets. It is worth pausing here, because this is where many explanations accidentally turn Bell's theorem into something it is not. Bell's theorem does not simply say particles influence each other faster than light. That is a tempting sentence, but it is too quick and too misleading. The theorem says that the combined assumptions of locality and pre-existing definite outcomes cannot both be maintained in the simple classical way. Something has to give. Different interpretations of quantum mechanics choose different things to give up or reinterpret. Some give up local hidden variables. Some keep a form of realism but accept non-local structure. Some focus on the role of measurement and avoid speaking about hidden properties altogether. The theorem itself does not politely hand us a single easy picture. It closes certain doors and leaves us standing in a hallway full of difficult ones. This is why Bell's result was so powerful. It did not solve every mystery, but it made the mystery sharper. Before Bell, one could imagine that quantum mechanics was just an incomplete summary of a more ordinary world underneath. After Bell, that ordinary world became much harder to defend. Not impossible in every conceivable form, because physicists are very creative and reality has many hiding places, but impossible if one insists on both locality and pre-written answers in the classical sense. The hidden cards, if they exist at all, cannot be the simple hidden cards Einstein hoped for. There is a quiet elegance in this. Bell did not need to know what hidden variables were. He did not need to propose the exact mechanism behind them. He simply asked what any local hidden variable theory must obey. That is like saying, I do not know who baked this cake, but if it was baked without flour, butter, eggs, or heat, it cannot have this texture. One does not need the full recipe to rule out an entire class of recipes. Bell showed that if reality is made of local hidden instructions, then the observed correlations must be limited. Quantum mechanics says those limits can be exceeded. Experiments then get to decide. The role of measurement settings is central. Alice and Bob must be able to choose between different measurements. If they always ask the same question, hidden card explanations can easily mimic the results. The glove example works perfectly when there's only one question. Is this the left glove or the right glove? Simple. But entanglement becomes distinctive when there are several possible questions, several measurement directions, and the particles still produce correlations across those choices. That is where local prearranged answers run into trouble. They cannot satisfy all the possible relationships at once as strongly as quantum mechanics does. A homely analogy may help, though it must be handled gently, like a sleeping hedgehog. Suppose two friends, Alice and Bob again, are trying to coordinate their answers to questions while sitting in separate rooms. They cannot talk once the questions begin. Beforehand, they can agree on a strategy. The host will ask each of them one of several possible questions, and each must answer yes or no. Their goal is to make their answers match or differ in certain patterns depending on which questions were asked. If Alice and Bob use only prearranged instructions, there is a limit to how often they can win this game. They can do well, but not perfectly. Quantum entanglement allows them to do better than any classical prearranged strategy, though still not in a way that lets them send messages. It is as if the universe allows a kind of coordination stronger than shared planning, but weaker than communication. This kind of game version has become very important in modern quantum information science. It turns the old philosophical debate into a task with rules, outcomes, and scores. The particles are not literally playing a game, of course. If they are being extremely quiet about it. But the structure captures the essence of Bell's theorem. Classical local strategies have a maximum score. Quantum entangled systems can exceed it. That excess is not an experimental inconvenience, it is the signature of non-classical reality. The word non-classical is useful because it does not try to say too much too quickly. It simply means the behaviour cannot be explained by the assumptions that worked so well for ordinary physics. Classical physics is full of definite objects, definite properties, and local causes. It is the world of falling apples, swinging pendulums, spinning wheels, and clocks that tick without asking philosophical questions. Quantum entanglement belongs to a different layer of description. It does not erase the classical world, but it tells us the classical world is not the deepest layer. The familiar furniture of reality is built on floorboards that creak in unexpected places. Bell himself understood the depth of the problem. He was not satisfied with vague statements about observation creating reality. He wanted clarity. He wanted to know exactly what assumptions were being made. In that sense, Bell continued Einstein's spirit even while showing that Einstein's preferred answer could not survive in its simplest form. Both men disliked careless thinking. Both wanted physics to say what it meant. Bell's theorem is sometimes described as a victory for Bohr over Einstein, but the truth is more interesting. It was Einstein's stubborn question, sharpened by Bell, that revealed the extraordinary nature of quantum correlations. Einstein may not have got the answer he wanted, but without his worry, we might not have asked the question so well. It is also important to understand what Bell's theorem does not depend on. It does not depend on human consciousness. Alice and Bob do not need to be people. They can be detectors, switches, computers, or carefully arranged devices sitting in separate laboratories. The particles do not wait for a mind to inspect the result. The relevant facts are physical records, measurement settings, and correlations. This matters because quantum mechanics is strange enough without adding unnecessary theatrical lighting. Entanglement does not require the universe to be thinking about us. It requires only that quantum systems behave according to the rules experiments reveal. Nor does Bell's theorem mean everything is connected in a vague spiritual soup. That phrase may sound comforting if one is half asleep beside a lava lamp, but it is not physics. Entanglement is specific. It is created under particular conditions. It can be tested with particular measurements. It can be lost through interaction with the environment. Bell's theorem concerns the correlations between entangled systems and what those correlations imply about locality and hidden variables. The real result is already startling. It does not need to be inflated into something fuzzier. A carefully measured quantum correlation is more wondrous than 1,000 vague claims about universal vibes, and far less likely to appear on a mug. The hidden cards picture then must be revised. In Einstein's preferred version, each particle carries a full set of local instructions. When measured, it reveals what was already there. Bell showed that such a picture cannot reproduce the quantum predictions. If experiments match quantum mechanics, then the hidden cards are not ordinary cards. Either the answers were not all written in advance, or the cards are not local in the way Einstein wanted, or the very idea of definite answers independent of measurement needs rethinking. The old envelope story has cracked. Something else is happening. Though whatever that something is, it remains disciplined by the rule that no usable message outruns light. This last point is worth returning to because it is so easy to lose. Bell's theorem reveals a kind of non-locality, but not a practical, faster-than-light signal. Alice cannot choose her result. Bob cannot read Alice's choice by looking only at his particle. Each side sees randomness locally. Only when they compare their records later, using ordinary communication, do the correlations appear. The universe allows a relationship that is stronger than classical local planning, but it refuses to turn that relationship into a cosmic telephone. It is as if nature says, yes, separateness is not quite what you thought, but no, you may not use this to send a shopping list to Saturn. The beauty of Bell's theorem lies partly in how little it needs. It does not require a giant particle accelerator. It does not require a complete theory of everything. It begins with paired systems, choices of measurement, and a comparison of results. From that modest setup, it reaches into the foundations of reality. The theorem tells us that the world cannot be both fully local and fully pre-written in the classical sense. It is a small logical lantern held up to an enormous dark room. For physicists, this was not merely unsettling, it was useful. Once entanglement could be understood through measurable correlations, it became something that could be certified, manipulated, and eventually used. Bell's work helped create the conceptual foundation for quantum information science. Today, violations of Bell-type limits are not just philosophical trophies. They help confirm the presence of entanglement, test the security of quantum communication, and explore the boundary between quantum and classical behaviour. What began as Einstein's objection became a practical diagnostic tool. The universe, having been accused of being incomplete, responded by becoming useful in an entirely unexpected way. One has to admire the confidence. Still, at the time Bell proposed his theorem, the result was not immediately celebrated by everyone. Foundational questions were not fashionable in every corner of physics. Many researchers were busy calculating, building, measuring, and applying quantum theory with enormous success. The question of what it all meant could seem like a distraction. Bell's work was profound, but it took time for its importance to be fully appreciated. This is often how deep ideas travel. They do not always arrive with trumpets. Sometimes they appear quietly in a paper, sit patiently on the shelf, and wait for the world to become ready. The experimental challenge was not simple. To test Bell's idea, physicists needed reliable sources of entangled particles, fast and independent choices of measurement settings, efficient detectors, and enough control to rule out ordinary loopholes. If the detectors missed too many particles, hidden variable explanations might still hide in the missing data. If the measurement choices were not made properly, some hidden coordination might be imagined. If the particles were not separated well enough, ordinary communication might be blamed. Each loophole was like a tiny door left ajar, and nature is too important a witness to question in a room full of open doors. But the path had been laid. Bell had done what Einstein's original argument needed. He had made it testable. No longer was the issue merely whether quantum mechanics felt complete, or whether spooky action seemed unacceptable. The question now had a practical form. Prepare entangled pairs, send the particles apart, choose measurements, record outcomes, compare the correlations, see whether the hidden card limit is obeyed or broken. If it is obeyed, Einstein's hope may survive. If it is broken, the universe is telling us something extraordinary, not in a loud voice, not with a flash of cosmic drama. But through small clicks in detectors, repeated thousands and millions of times, forming a pattern no local hidden instruction story can explain. That is the quiet power of physics. It can take an argument about reality itself and turn it into a sequence of careful measurements. It can ask the universe a question so subtle that ordinary language nearly trips over it, and still receive an answer. And the answer, when experiments finally became precise enough to ask properly, did not restore the old comfort. It did not hand the hidden cards back to Einstein with a reassuring smile. It pointed instead toward the stranger possibility, the one quantum mechanics had been whispering all along. Entangled particles really do produce correlations beyond the reach of local pre-written explanations, and the first clear experimental steps toward that conclusion would turn Bell's quiet theorem into one of the most remarkable confirmations of quantum theory ever performed. The first experiments that tried to answer Bell's question did not look like the sort of thing that should disturb reality. There were no collapsing stars, no roaring engines, no dramatic doorway into another dimension. There were laboratories, light sources, detectors, cables, switches, tables, mirrors, and human beings trying very carefully not to let dust, heat, bad alignment, or a suspiciously loose connection ruin the day. And yet, inside those quiet rooms, physicists began asking one of the deepest questions ever put to nature. Are the results of quantum measurements written into particles from the beginning, like hidden notes tucked into envelopes, Or does the world really produce correlations that cannot be explained by any ordinary local plan? This is one of the loveliest things about physics. The question may sound grand enough to belong among philosophers, late-night stargazers, and people who have had slightly too much coffee, but the answer has to come through equipment. A detector clicks or it does not. A photon is counted or it is lost. A setting is chosen, a result is recorded, and after thousands upon thousands of trials, a pattern begins to appear. The universe rarely explains itself in complete sentences. It prefers data, which is a little less cosy, but often more honest. The earliest tests of Bell's idea were built around pairs of particles that could show entanglement in a measurable way. Photons became especially useful because they are easy to send over distance, and their polarization can be measured with carefully arranged filters. Polarization is a property of light related to the orientation of its electromagnetic vibration, although for our purposes we can think of it more gently as a kind of direction associated with the photon. A detector can be set up to ask a photon a particular polarization question, and the photon gives one of a small set of possible answers. One photon alone may look random, but if two photons are entangled, the relationship between their answers can reveal the deeper pattern Bell had described. The general procedure sounds simple when said quickly. Create entangled pairs. Send one photon to Alice and the other to Bob. Let Alice and Bob choose how to measure their photons. Record the outcomes. Repeat many times. Compare the results. See whether the correlations stay within the limits allowed by local hidden instructions, or whether they cross into quantum territory. That sounds neat and tidy, like a recipe. Unfortunately, real experiments are less like following a recipe and more like trying to bake a souffle on a train during a mild earthquake while someone keeps changing the oven temperature. The first major experimental steps came in the 1970s. Physicists John Clauser and Stuart Friedman performed an important test using pairs of photons emitted by calcium atoms. The setup was not perfect by modern standards, but it was a remarkable achievement for its time. They measured correlations between the photons and found results in agreement with quantum mechanics, not with the local hidden variable limit Bell had derived. This was a striking sign that Einstein's hidden cards were in trouble, not entirely defeated yet because careful scientists are rarely satisfied with one experiment and a dramatic shrug, but definitely in trouble. It is worth imagining the mood of such an experiment. There is a source at the centre producing pairs of photons. The photons travel in opposite directions toward measurement devices. Those devices are set at chosen orientations, and each photon either passes in a way that produces a recorded result or it does not. The results are not meaningful one by one in the way a tossed coin is not very meaningful if you only toss it once. But when enough results accumulate, the correlation can be compared with what different theories predict. If the particles carried ordinary hidden cards, the pattern should respect Bell's boundary. If quantum mechanics is right, the pattern can step beyond it. That step beyond the boundary is what people often mean when they say experiments proved the impossible. Of course, nothing truly impossible happened, because if it happened, it was possible in nature. What was proved impossible was a particular picture of reality. The picture in which particles carry complete local instructions and simply reveal them when measured could not explain the observed patterns. The impossible thing was not entanglement itself. The impossible thing was keeping all our old assumptions intact. But experiments do not merely have to find a result. They must also close escape routes. In the case of Bell tests, these escape routes are called loopholes, which sounds almost cute, as if the universe were a small animal trying to wriggle out of a cardboard box. But the loopholes were serious. If a test had weaknesses, then someone could argue that the apparent violation of Bell's limit did not truly rule out local hidden variables. Perhaps the detected photons were not a fair sample of all the photons. Perhaps the measurement settings were not changed quickly enough. Perhaps some ordinary signal could have passed between the two sides. Perhaps the experiment, like a tired person assembling furniture at midnight, had left out a crucial piece. One major issue was the detection loophole. In an ideal experiment, every particle sent from the source would be detected and counted. In practice, detectors miss things, photons get lost, equipment is imperfect. If too many particles are missed, a hidden variable theory might argue that the detected sample is biased. Maybe the particles that were counted happened to be the ones that produced quantum-looking correlations, while the lost ones would have restored a classical pattern. This sounds a bit like claiming that all the missing socks would have proved your laundry system works perfectly if only they had stayed to testify. Still, in science, one must take such possibilities seriously until the experiment rules them out. Another issue was the locality loophole. To truly test Bell's idea against local hidden variables, Alice's measurement choice and outcome should be separated from Bob's in such a way that no signal travelling at or below the speed of light could coordinate them during the measurement. If the devices are too close together, or if the measurement settings are fixed too early, someone might imagine a hidden influence moving between them in time to produce the result. To close this loophole, experimenters need distance, speed, and careful timing. The measurement choices must be made while the particles are already on their way, and the two sides must be far enough apart that ordinary communication cannot explain the correlations. That is easy to say, and not especially easy to build, rather like saying one should simply keep the kitchen clean. In the early 1980s, Alain Aspect and his colleagues in France performed a series of experiments that became famous because they addressed the locality issue more directly than earlier tests. They used entangled photons and changed the measurement settings rapidly, while the photons were in flight. The results again agreed with quantum mechanics and violated Bell-type limits. These experiments were a turning point. They did not close every possible loophole by modern standards, but they made the case much stronger. The universe, when questioned more carefully, continued to give the same unsettling answer. Picture the photons racing outward from their source. On each side, the measuring device can be set in different ways. The choice must happen quickly enough that one side cannot simply inform the other through an ordinary signal. The particles arrive, detectors register outcomes, and later the records are brought together. Alice's record alone looks random. Bob's record alone looks random. Nothing in either local stream of results says, here is a message from the other side. But compare them, and the pattern is there. Stronger than local hidden instructions allow. Not loud, not theatrical. Just quietly, repeatedly, beyond the classical limit. This is the part that can feel almost disappointing at first. We expect the proof of quantum weirdness to look weird. We want a particle to glow green, or a detector to whisper a warning, or a laboratory mouse to briefly understand philosophy. Instead, the evidence arrives as statistics, counts in columns, correlations between settings, repeated trials, but that is also what makes it powerful. Statistics are not a weakness here. They are the language of the phenomenon. Quantum mechanics does not say each individual outcome will reveal the secret. It says the pattern across many outcomes will. Reality, in this case, is not shown by a single event, but by the shape of many events together. Over the following decades, experiments became more precise and more ambitious. Scientists used better photon sources, improved detectors, longer distances, and new methods for choosing measurement settings. They also tested entanglement with different physical systems, not only photons but atoms, ions, superconducting devices, and other quantum platforms. Each system brought its own strengths and its own difficulties. Photons travel well but can be lost. Ions can be detected efficiently, but are harder to separate over long distances. Solid-state systems can be engineered on chips, but often require extremely low temperatures and careful isolation. If quantum experiments were houseplants, they would be the kind that require exact humidity, indirect light, whispered encouragement, and perhaps a personal calendar. The goal was not simply to repeat the same experiment for tradition's sake. Each new test helped close loopholes, increase confidence, and explore how entanglement behaves in different settings. A central question remained. Could one experiment close the major loopholes at the same time? For many years, tests tended to close one loophole well while leaving another less tightly controlled. Photon experiments could address locality over long distances, but often suffered from detection inefficiency. Matter-based experiments could detect particles more efficiently, but had difficulty achieving the separation needed to close the locality loophole. The perfect Bell test was like a very picky guest. It wanted everything arranged just so. By the 21st century, technology had improved enough for stronger tests. In 2015, several groups reported experiments often described as loophole-free Bell tests. They used different approaches, including entangled electron spins in diamond effects and entangled photons with highly efficient detection. These experiments were designed so that the measurement choices were made rapidly and independently, the particles or systems were suitably separated, and the detection efficiency was high enough to avoid the old sampling concern. The results again supported quantum mechanics. The hidden local instruction picture had fewer and fewer places to hide, and the places that remained were no longer ordinary physics so much as extremely philosophical cupboards. This does not mean every possible loophole in the broadest imaginable sense is closed forever. Science is careful with absolute statements, and physicists can always imagine exotic assumptions if they are determined enough. For example, one can question whether the measurement choices are truly free or whether some deep hidden connection in the past arranged everything, including the experimenter's decisions. This is sometimes called superdeterminism. It is not impossible as a logical idea, but it comes with a heavy price. It suggests that the apparent freedom to choose measurement settings is itself correlated with the hidden variables in just the right way to fake quantum results. That is a very large claim to keep the old hidden card picture alive, rather like explaining a missing biscuit by proposing that the entire history of the universe conspired to make your hand reach the tin at precisely the right moment. Physicists have even performed Bell tests using cosmic sources to help choose measurement settings. The idea is wonderfully grand. Instead of letting a small electronic device decide how to set the detectors, use light from distant stars or quasars, objects whose light began travelling toward Earth long before the experiment. If the measurement choices are influenced by ancient cosmic events, then any hidden coordination would have to reach far back into the history of the universe. These cosmic Bell tests do not remove every philosophical escape route, but they push certain conspiratorial explanations into increasingly uncomfortable territory. The universe can still be stubborn, but at some point one begins to suspect it is not hiding ordinary instruction cards after all. All of this raises a useful question. What exactly did these experiments prove? They did not prove that measurement results can be used to send messages faster than light. They did not prove that human consciousness creates reality. They did not prove that love is a quantum field, though one must admit the phrase would sell well on a candle. What they showed is more precise and more important. They showed that the correlations predicted by quantum mechanics are real, and that no theory based on local hidden variables in Bell's sense can explain them. The world cannot be both local and pre-written in the simple classical way. That statement may feel less dramatic than saying impossible, but it is far more powerful. It tells us which picture of reality fails. It does not hand us a fully intuitive replacement. Quantum mechanics gives the predictions and the structure, but the deeper meaning remains open to interpretation. Some interpretations say the outcomes are not definite until measurement. Some say all possible outcomes occur in branching worlds. Some say there is a real non-local guiding structure beneath the quantum wave. Some avoid the question by focusing only on observed relations. Bell experiments do not force everyone into one philosophical camp. They do something cleaner. They rule out a large family of comfortable classical explanations, and the experimental result has become more than a foundational curiosity. Bell violations are now tools. In quantum information science, demonstrating non-classical correlations can help certify entanglement. It can support secure communication protocols where the security depends on the impossibility of classical mimicry. It can test devices whose internal workings may not be trusted. This is a remarkable turn. What began as a debate about whether quantum mechanics was complete became a practical resource. The thing Einstein found suspicious now helps us design new ways to process and protect information. It is as if a loose thread in the sweater of reality turned out to be connected to an entire hidden loom. Still, the emotional force of the experiments lies in their quiet refusal to restore common sense. Many people expected, or at least hoped, that the strangeness of entanglement would eventually dissolve into something ordinary. Perhaps particles had hidden settings. Perhaps measurement only revealed what was already there. Perhaps the quantum fog was just our ignorance. Bell tests made that hope much harder to sustain. The fog was not merely in our heads. The correlations really do exceed what local hidden instructions can do. Nature is not confused. We were. That may sound unsettling, but it is also a kind of liberation. Science does not ask the universe to match our habits. It asks what actually happens. Our intuition was built in a middle-sized world of chairs, rain, food, faces, falling objects, and the ongoing mystery of why charges vanish exactly when needed. It was not built for entangled photons. So when experiments reveal that our ordinary assumptions fail, it is not a defeat. It is an invitation. We are allowed to update our imagination. There is also something deeply patient about the history. Einstein raises a concern in the 1930s. Bell sharpens the concern in the 1960s. Experiments grow stronger over the following decades. By the time loophole-free tests arrive, generations of physicists have contributed mirrors, detectors, sources, timing systems, arguments, corrections, and refinements. The proof of the impossible was not a single heroic moment. It was a long tightening of a question until nature had less room to answer ambiguously. That is often how science works. Not as one thunderclap, but as rain filling a river. When we say experiments prove the impossible, then we should hear it gently. They proved that a familiar idea of what must be possible was wrong. They proved that entangled particles do not behave like ordinary objects carrying hidden cards. They proved that the universe can produce correlations beyond local classical explanation, while still protecting the rule that no usable message travels faster than light. They proved that quantum mechanics, strange as it seems, is not merely a clever calculation trick. Its strangeness shows up in the world, in laboratories, in detectors, in repeated records gathered by people careful enough to ask the question properly. And perhaps the most surprising part is how ordinary the evidence looks once collected. Rows of results, timings, detector counts, statistical patterns, no fireworks, no portal, no particle pausing to say, by the way, Einstein was nearly right to worry. Yet the meaning is enormous. The old picture of separable little things with independent pre-written properties cannot be the whole story. At the quantum level, the relationship between systems can be more fundamental than the individual answers we expect them to carry. From here, the puzzle becomes even more delicate. If entangled particles produce correlations stronger than local hidden cards allow, but those correlations cannot be used to send messages faster than light, then what exactly is being shared? What kind of information exists in the pair, but not in either particle alone? Why does each side see only randomness until the results are compared? And how does the universe allow such strong connection, while still refusing to let anyone turn it into an instant cosmic telegram? Now we arrive at the part of entanglement that often causes the most mischief, because it sounds as if nature has left a secret door unlocked. If two particles can be connected across distance, and if measuring one is tied to what we later find about the other, then surely we can use that connection to send a message. Surely Alice can tap her particle in one laboratory, and Bob can read the result in another. Surely someone, somewhere, has already tried to use this to send an instant note saying, "Put the kettle on, I have arrived 3 galaxies early." And this is where quantum mechanics gives one of its most elegant little refusals. Entanglement creates correlations, but not controllable signals. It links measurement outcomes in a way that defies ordinary hidden card explanations. But it does not let anyone choose those outcomes. It makes the pair behave as one shared quantum system, but it does not provide a faster-than-light communication service, no matter how many customer support forms one files with the universe. This is called the no-signaling principle. The name is not especially decorative, but it says something important. Even though entangled particles can show correlations stronger than anything allowed by classical local hidden instructions, those correlations cannot be used to transmit usable information faster than light. Alice can measure her particle, Bob can measure his. Later, when they compare their records through ordinary communication, they can see the remarkable pattern. But Bob cannot look at his record alone and know what Alice chose to do. His local results look random. Alice's local results look random. The secret is not in either list by itself, it is in the comparison. This is subtle enough that it deserves to be handled slowly, like a tray of teacups crossing a room with an enthusiastic dog nearby. Let us imagine Alice and Bob again, because by now they have become the patient household names of quantum explanation. An entangled source sends one particle to Alice and one to Bob. They are far apart. Alice chooses a way to measure her particle. Bob chooses a way to measure his. Each receives an outcome. If Alice looks only at her own results, she sees a random sequence. If Bob looks only at his own results, he sees a random sequence too. Nothing about Bob's sequence says whether Alice measured this way or that way. Nothing in Alice's sequence says what Bob did. Alone, each side looks like noise. But later, Alice and Bob bring their notebooks together. Perhaps they meet in a conference room. Perhaps they send the data by ordinary radio or fibre optic cable. Perhaps they compare results over a video call where one microphone keeps refusing to behave. Once they line up the records and sort the outcomes according to the measurement choices, the pattern appears. The correlations match what quantum mechanics predicts. They can violate Bell-type limits. They show that the pair was not behaving like two ordinary objects carrying hidden local instruction cards. Yet none of that was visible to either person before the comparison. This is the heart of the no-signaling mystery. Entanglement seems to reach beyond classical separateness, but it hides its message in a place no one can access alone. The relationship is real, but it is not a usable telegram. It is like having two books whose sentences only reveal a pattern when read side by side, while each book alone looks like a pile of randomly selected words. You cannot send a message by choosing what your book says, because you do not control the words that appear. Only later, when the two books are compared, does the hidden structure become clear. And even then, the structure was not a message chosen by either reader. It was a correlation produced by the shared quantum state. This distinction between information and signaling is essential. In everyday life, we often use the two words as if they are almost the same. If I send you information, I have signaled something. If your phone buzzes, a message has arrived, unless it is only a weather alert telling you that the sky may behave like weather. But in quantum physics, information can be present in the structure of a joint system without being locally accessible as a signal. Entangled particles contain information in their correlations. The pair has a shared description, but neither particle alone carries a readable message about the distant measurement choice. It helps to think again about randomness. Suppose Bob receives a long list of outcomes from his detector. To him, the list might look like heads, tails, heads, heads, tails, tails, and so on, though of course the real outcomes depend on the property being measured. If Alice decides to measure her particle one way, Bob's list still looks random. If Alice decides to measure another way, Bob's list still looks random. If Alice does nothing at all, Bob's list still looks random. Bob cannot tell the difference from his data alone. The randomness protects relativity. It prevents entanglement from becoming an instant communication machine. That may sound like a technical inconvenience, but it is actually a deep harmony between quantum mechanics and relativity. At first glance, entanglement and relativity seem to be pulling in different directions. Relativity says no usable influence or information can travel faster than light. Entanglement says separated systems can show correlations that cannot be explained by ordinary local hidden variables. One might expect these ideas to collide like two shopping trolleys, with one wobbly wheel each. Yet the no-signalling principle keeps them from crashing. Quantum mechanics allows non-classical correlation, but it prevents controllable faster-than-light communication. The world is stranger than Einstein wanted, but not lawless. Still, the word information remains slippery. What information does an entangled pair contain? Not information in the ordinary sense of a message written in one place and read in another. Rather, it contains relational information. Some facts belong to the pair as a whole. They do not belong fully to Alice's particle or Bob's particle alone. This is one of the most important shifts entanglement asks us to make. We are used to thinking that a complete description of a whole system can be built by fully describing each part. Describe every brick, and you describe the wall. Describe every ingredient, and you describe the soup, although the soup may still have opinions. But quantum mechanics says that, for entangled systems, the whole can contain information that is not present in the separate descriptions of the parts. That sounds almost philosophical, but it has practical meaning. If Alice has her particle and Bob has his, neither can reconstruct the full entangled state from their local particle alone. The information about the relationship is distributed between them. It exists in correlations that require both records to reveal. This is why entanglement is such a valuable resource in quantum information science. It allows information to be shared and structured in ways classical systems cannot imitate. It can support secure communication, teleportation of quantum states, and certain forms of quantum computation. Entanglement is not merely weird, it is useful weirdness, which is the sort of weirdness physicists often become very fond of. In ordinary communication, a message must be controllable. If I want to send you the word yes, I must be able to choose yes rather than no. If I want to send a shopping list, I must be able to choose bread, milk, and biscuits, rather than accidentally sending umbrella, radiator, and philosophical despair. Entanglement does not give Alice that control over her measurement result. She can choose what kind of measurement to perform, but she cannot choose the outcome she receives. The outcome is random according to quantum rules. Since Bob's local results also remain random, Alice's choice cannot be decoded by Bob as a message. This point also explains why the phrase instant collapse can be misleading if taken too literally. In some descriptions of quantum mechanics, when Alice measures her particle, the shared state is said to collapse, and the description of Bob's particle changes accordingly. That sounds like something physical has rushed across space. But the meaning depends on interpretation. In a practical sense, Alice has updated what she can predict about Bob's result if he measures in a corresponding way. The joint description changes because a measurement outcome has become part of the record. But Bob's local experience does not suddenly show a detectable disturbance. His particle does not flash, beep, or receive a tiny note saying, "Alice has looked now, please adjust accordingly." The correlations become meaningful only when the results are compared. One way to keep this straight is to separate prediction from communication. When Alice measures her particle, she may now be able to predict something about Bob's result if Bob measures in the right way. But Bob does not receive Alice's prediction. From Bob's side, nothing usable has arrived. Alice's knowledge has changed, the joint accounting has changed, but no signal has been sent. This is similar, very loosely, to opening one of the two glove boxes and learning what glove is far away, except entanglement is much stranger because the outcomes are not simply pre-written in the classical way. The useful part of the glove analogy is that learning can happen instantly without a message travelling. The misleading part is that gloves had definite identities all along. Quantum particles do not fit so politely into that story. The no-signalling principle is also why entanglement can coexist with the everyday order of cause and effect. Imagine if Alice could use entanglement to send messages instantly to Bob across any distance. Relativity would be in trouble. In some frames of reference, depending on motion, the order of distant events can differ. A faster-than-light signal could lead to situations where effects appear before causes. With enough cleverness, one might build causal loops, send warnings into the past, or at least ruin the scheduling department of the universe beyond repair. Physics seems very committed to preventing this. Entanglement tiptoes right up to the edge of faster-than-light weirdness, smiles politely, and then refuses to hand over a working telephone. This refusal is not a bug. It is one of the reasons quantum theory is so carefully structured. The randomness of individual outcomes is not just a nuisance. It is part of the consistency of the theory. It allows entanglement to produce stronger than classical correlations without permitting controllable, faster-than-light communication. Nature seems to have arranged a rather delicate bargain. You may have correlations deeper than classical physics allows, but you may not use them to send a message before light could get there. The universe gives with one hand and gently removes the intergalactic texting plan with the other. There is another interesting consequence. Since the correlations require comparison, ordinary classical communication is still needed to make use of entanglement. Alice and Bob must exchange information about their measurement settings and outcomes through normal channels. Those channels obey the speed limit of light. This is true even in quantum teleportation, which we will come to soon. Entanglement is necessary for teleporting a quantum state, but it is not sufficient by itself. A classical message is also required. Without that ordinary message, the receiver cannot complete the process. This is one of those facts that takes the science fiction glamour down by one notch, and the real scientific elegance up by several. Now, if entanglement cannot send messages faster than light, one might wonder why people call it non-local at all. The answer is that non-locality in this context does not mean ordinary communication across distance. It means the correlations between outcomes cannot be explained by local hidden variables. The measurements behave as though the pair is described by one shared quantum state that does not break into independent local pieces. That is the non-local feature. It is not a beam of influence you can aim. It is not a force weakening with distance. It is a failure of the old idea that all observable correlations must come from either local causes or shared hidden instructions established in the past. This is a different kind of connection from the ones our senses evolved to understand. A rope connects two buckets. Pull one and the other moves. A sound wave connects a bell to your ear. Strike the bell and vibrations travel through air. A wireless signal connects a phone to a tower, assuming one is not standing in the exact corner of the house where technology goes to sulk. These are ordinary connections. They involve signals, forces, or physical carriers moving through space. Entanglement is not like that. It is a connection in the quantum state, revealed in correlations constrained by randomness and protected from becoming a usable faster-than-light signal. This is why entanglement can feel like a message that cannot be read. The pair contains a kind of shared information, but the information is locked in the joint pattern. Alice has one half of the lock, Bob has the other. Neither half alone opens anything meaningful. Only later, when the data are brought together, does the structure reveal itself. In this sense, entanglement is less like a telephone, and more like a pair of puzzle pieces sent to different places. Each piece may look irregular and meaningless on its own. When placed together, the shape appears. But no one can use one piece alone to tell the other piece what to become. This feature becomes especially important in secure quantum communication. Some protocols use entanglement to help detect eavesdropping. The idea is not that messages are sent faster than light, but that quantum correlations are sensitive to measurement and disturbance. If an outside party tries to intercept or measure the quantum systems in the wrong way, the correlations change. Alice and Bob can check for that disturbance by comparing part of their data. If the pattern looks wrong, they know the channel may not be secure. This is a practical use of quantum weirdness, but again, it depends on ordinary communication and careful comparison. Even quantum secrecy has paperwork. The relationship between entanglement and information also changes how physicists think about measurement. When a measurement occurs, information about a quantum system becomes recorded in a larger system, such as a detector or environment. In entangled systems, measurement does not simply uncover a property belonging privately to one particle. It helps produce a definite outcome within a shared structure. This is why the correlations are so strange. The individual outcomes are not pre-existing entries in a local instruction book, yet they are not unconnected accidents either. They are random locally and ordered jointly. That phrase is worth resting with for a moment. Random locally, ordered jointly. It is one of the cleanest ways to hold the no-signalling mystery in mind. Random locally means Alice cannot control her result, and Bob cannot read Alice's choices from his own result. Ordered jointly means that when their results are later compared, the pattern reveals the entangled state. The two facts must be held together. If we remember only the order, we may mistakenly imagine faster than light signalling. If we remember only the randomness, we may miss the extraordinary correlations. Entanglement lives in the balance between them. That balance also helps explain why entanglement is not simply ignorance. In classical ignorance, the information exists somewhere, even if we do not have it. The card in the envelope is already red or blue. The coin under the cup is already heads or tails. The biscuit tin is already empty or not, though experience suggests caution before hope. In quantum entanglement, the correlations cannot be explained as ignorance about pre-existing local values. Bell experiments show that. The information is not hidden in the old way. It is woven into the joint state in a way that only appears through measurement statistics. The word woven is gentle, but we should keep it grounded. Entanglement is not a physical thread stretched between particles. If one particle travels farther away, we do not imagine the thread becoming longer and longer, waiting to twang when measured. That image is charming but dangerous. A thread suggests tension, force, and a path through space. Entanglement is not known by tugging. It is known by comparing outcomes. The bond is not a material connector. It is a feature of the mathematical and physical description of the combined system. It is real because it has measurable consequences, but it is not real in the way a string, wire, or bridge is real. This distinction matters when people ask where the information is stored. If Alice's particle alone does not contain the full information, and Bob's particle alone does not contain it either, then where is it? The best answer is that the information is non-locally encoded in the joint state. That phrase may sound like it has arrived from a very serious conference badge, but the meaning is straightforward. The information belongs to the whole arrangement, not to either part alone. It is not located at Alice's detector. It is not located at Bob's detector. It is in the correlations between them, which are revealed only when both sides are considered together. In the broader view of physics, this has become a major theme. Information is not just a bookkeeping convenience. It has physical meaning. It matters in thermodynamics, black holes, quantum computing, and the foundations of space-time. Entanglement sits at the center of that shift, because it shows that information can be relational at the deepest level. What can be known about a whole system is not always reducible to what can be known about its pieces. This is a quiet revolution in how we think about reality. It says the universe is not merely made of things, but also of structured relationships among things. And yet, for all this depth, the practical rule remains simple. Entanglement alone cannot send a message. If Alice wants Bob to know something, she still has to use a classical channel. She can phone him, email him, flash a lamp, send a radio wave, or write a note and attach it to a surprisingly patient pigeon, but none of these outruns light. Entanglement can enrich what they do together once they share data. It can make certain tasks possible that classical resources cannot perform in the same way, but it does not let either person bypass the causal order of the universe. So the no-signalling mystery is not a disappointment. It is the reason entanglement is both strange and stable. It gives us a world where separateness is not as simple as it looks, but where cause and effect do not collapse into nonsense. It lets quantum systems share a state across distance, yet keeps local observations safely random. It lets Bell experiments reveal that hidden local cards cannot explain reality, yet prevents anyone from using that revelation to send tomorrow's lottery numbers into yesterday's notebook, which is probably for the best, though one can understand the temptation. As we move deeper, this balance becomes the foundation for one of the most famous and often misunderstood applications of entanglement. If a shared quantum state can hold information between distant systems, and if ordinary communication must still be used, then there is a way to transfer the state of one quantum system onto another without carrying the original particle across the distance. The word for this is teleportation, which sounds as if we are about to vanish in a blue shimmer and reappear beside the biscuits. The real version is quieter, stricter, and in many ways more astonishing, because what moves is not the object itself, but the delicate quantum information describing its state. This is where the word teleportation quietly walks into the room, carrying far more drama than the experiment itself usually shows. For most of us, teleportation means a person steps into a glowing chamber, makes a brave expression, dissolves into sparkling mist, and reappears somewhere else looking slightly surprised but otherwise unharmed. It is the dream of avoiding airports, traffic, queues, and that one suitcase wheel that only works when it feels emotionally supported. In science fiction, teleportation moves things. Bodies, ships, sandwiches, occasionally people who really should have read the safety instructions first. In quantum physics, teleportation is much more precise and much stranger. It does not move a thing in the ordinary sense, it moves a state. That sounds less exciting at first, as if we have replaced a starship with a filing cabinet. But the state of a quantum system is not a minor detail. It is the full description of what that system is, as far as quantum physics is concerned. If you know the quantum state of a particle, you know the structure of its possible measurement outcomes. You know how it will behave in experiments. You know the delicate information that makes it that particular quantum system rather than another. So when physicists say quantum teleportation transfers a state, they are not talking about sending a label, a name, or a small polite note. They are talking about transferring the very quantum description from one physical system to another. The key is that the original object does not travel through space. Nothing zips invisibly from Alice to Bob faster than light. No tiny particle slips into a secret tunnel and emerges elsewhere wearing a hat. Instead, quantum teleportation uses entanglement, measurement, and ordinary communication together to make Bob's distant particle take on the state that Alice's original particle had. At the end, the state has been transferred, but the original version no longer remains with Alice. This is not copying. It is relocation of quantum information from one system to another. That distinction matters enormously because quantum states cannot simply be copied at will. This is one of the important rules of quantum mechanics. If you have an unknown quantum state, you cannot make a perfect duplicate of it while leaving the original untouched. This is sometimes called the no cloning principle, which sounds like a rule posted in the break room of a very cautious science facility. In ordinary life, copying information is easy. You can copy a recipe, a photograph, a document, or a message saying please buy more biscuits, which in some households may qualify as emergency communication. Classical information can be duplicated because reading it does not necessarily destroy it. A printed word stays where it is after you look at it. Quantum information is not like that. To find out the full state of an unknown quantum system, you would have to measure it, but measurement changes the system and gives only certain kinds of outcomes depending on what you ask. You cannot gently peek behind the quantum curtain, write down the entire unknown state, and then put everything back as it was. Nature does not allow that kind of casual photocopying. This is why quantum teleportation is not simply scanning a particle and rebuilding it somewhere else from a complete instruction sheet. There is no full instruction sheet Alice can read without disturbing the original. The process has to be more subtle. Let us set the scene gently. Alice has a quantum particle in an unknown state. Bob is far away. Alice wants Bob to end up with a particle in that same state. The obvious method would be to send the particle itself to Bob, perhaps through a fibre, through empty space, or by placing it very carefully in a small box marked fragile, and hoping the postal service has improved since last time. But suppose Alice cannot send the particle directly, or suppose the goal is to transfer the state without moving the original carrier. Quantum teleportation offers a way. Before the teleportation begins, Alice and Bob must share an entangled pair. One particle of this pair is with Alice and the other is with Bob. These two particles have a shared quantum state, the kind of deep relationship we have been slowly circling throughout this journey. They are not carrying a usable message between them, they are not a faster-than-light telephone, but they do contain correlations that can be used as a resource. Entanglement here is like a prepared bridge, though not a bridge that matter walks across. It is more like a shared structure that makes the transfer possible once the right measurement and the right ordinary message are added. So Alice now has two particles near her. She has the original particle whose state she wants to teleport, and she has her half of the entangled pair. Bob has the other half of the entangled pair. The clever step is that Alice performs a joint measurement on her two particles. This measurement does not simply inspect them separately, it asks a question about their combined quantum relationship. In doing so, it entangles the original particle with Alice's half of the pair and produces a result. That result is random, as quantum measurement results tend to be. Alice cannot choose it. She cannot decide in advance which outcome she would prefer, any more than one can politely ask toast to land butter side up during an emergency. The joint measurement has an important effect. It destroys the original state at Alice's location. That may sound alarming, but it is exactly what must happen if quantum information cannot be copied. The state is not left behind while another copy appears elsewhere. The original is consumed by the measurement process. This is one of the reasons quantum teleportation does not violate the no-cloning principle. At the end, there is one version of the state, not two. It has moved from Alice's original particle to Bob's particle, but only after the process is completed. After Alice's measurement, Bob's distant particle is now related to the original state, but not necessarily in the exact form yet. It may need a correction. Which correction is needed depends on Alice's measurement result. And here the ordinary unglamorous part enters. Alice must send Bob a classical message telling him which result she obtained. This message travels through normal means. It could be a light pulse, an electronic signal, a phone call, or in a very slow and charming version, a note carried by someone with comfortable shoes. It cannot travel faster than light. Until Bob receives that classical information, he cannot finish the teleportation. This is the piece that keeps quantum teleportation from becoming faster than light communication. Entanglement is necessary, but it is not enough. Alice's measurement changes the overall relationship, but Bob cannot use his particle alone to know what has happened. Without Alice's ordinary message, Bob's particle does not reveal the teleported state in a usable way. He has something, but not yet the completed thing. The classical message tells him what operation to perform on his particle so that it takes on the original state Alice wanted to send. Once he applies the correct adjustment, the teleportation is complete. So the recipe, spoken without formulas and without the sleep-disturbing clatter of mathematical notation, is this. Alice has a quantum state she wants to transfer. Alice and Bob already share entanglement. Alice performs a joint measurement on the original system and her half of the entangled pair. Alice sends the measurement result to Bob through ordinary communication. Bob uses that information to adjust his half of the entangled pair. Bob's particle then becomes the carrier of the original state. The state has moved. The original has been erased. No matter has travelled across the gap. No signal has outrun light. And no one has stepped into a glowing booth, which is probably a relief for everyone involved. It is worth slowing down over how strange this really is. Bob's particle did not begin with the state Alice wanted to send. It was part of an entangled pair. Alice's original particle did not physically travel to Bob. Alice did not learn the full unknown state and then describe it to Bob. In fact, she could not have done so. Instead, the entanglement and the joint measurement allow the state to be transferred through a process where the information is never fully exposed in a classical way. The state is not read like a sentence and rewritten elsewhere. It is moved by using the structure of quantum correlations. This makes quantum teleportation one of the clearest examples of entanglement as a resource. In the earlier discussions, entanglement might have seemed mainly like a puzzle, a strange feature that bothered Einstein and challenged hidden variables. Here it becomes something you can spend. Not spend in the sense of money, although quantum laboratories do have a way of making funding committees breathe deeply. Spend in the sense that the entangled pair is consumed by the process. Once used for teleportation, that particular entanglement is no longer available in the same way. It has done its job. The shared state has enabled the transfer of another state. The word resource is very important in modern quantum science. A century ago, entanglement looked almost like an embarrassment, a sign that quantum mechanics might be saying something too strange to accept. Later, Bell's theorem made it a test of reality. Today, it is treated as something valuable that can perform tasks impossible for ordinary systems. Entanglement can help with secure communication. It can link components of quantum computers. It can distribute quantum information across networks. And in teleportation, it allows the transfer of a quantum state from one physical carrier to another without directly sending the carrier itself. This does not mean teleportation is easy. Real quantum teleportation experiments require careful preparation, clean entanglement, reliable measurement, and protection from decoherence. Photons can be teleported in terms of their polarization state. Atomic states can be teleported between matter systems. Researchers have performed teleportation over laboratory distances, through optical fibers, across free space, and in systems relevant to future quantum networks. The details vary depending on the physical platform, but the principle is the same. Entanglement plus joint measurement plus classical communication allows a quantum state to be reconstructed at a distant location. The first successful demonstrations of quantum teleportation were not teleporting large objects. They were teleporting states of small quantum systems. This can sound underwhelming if one comes expecting a transported cat, though the cat would probably object to being included. But in physics, moving the state of a single photon or atom is already profound. The quantum state is fragile. It cannot be copied, it may be unknown, and yet, using entanglement, it can be transferred. That is not a small trick. It is a deep rearrangement of what it means to move information. People sometimes ask whether quantum teleportation could one day teleport humans. The honest answer is that this is not what quantum teleportation is built for, and the difficulties are not merely engineering details waiting for a sufficiently determined person with a clipboard. A human body contains an enormous number of particles in a wildly complex state, constantly interacting with the environment. To teleport such a state in the quantum sense would require controlling and transferring the complete quantum information of every relevant part, while also destroying the original, avoiding decoherence, and somehow handling a complexity so vast it makes ordinary biological detail look like a shopping list. It is not just hard. It belongs to a different universe of hard. The kind of hard that makes climbing a mountain look like tidying a drawer. More importantly, the quantum teleportation used in laboratories does not move matter. Bob must already have a particle or system that will receive the state. The receiving system becomes the new carrier. For a person, that would mean having a complete physical system at the destination ready to take on the state, which brings in questions far beyond current science and straight into philosophy, identity, continuity, and whether the teleported version would still complain about early morning meetings. It is a fascinating topic, but it is not what current quantum teleportation means. The real phenomenon is about transferring quantum states between controlled systems, not beaming people across rooms. And again, no faster-than-light travel is involved. This is worth repeating because the word teleportation keeps trying to smuggle speed into the conversation. The classical message is essential, and it obeys the ordinary speed limit. Bob cannot complete the process until Alice's message arrives. If Bob is on the moon, he waits for the message. If Bob is near Mars, he waits longer. If Bob is very far away, he has time to make tea, finish the tea, wash the cup, wonder about his life choices, and then perhaps receive the necessary information. Entanglement provides the quantum connection, but classical communication provides the usable instruction. This blend of quantum and classical ingredients is one of the most elegant aspects of the process. Quantum teleportation does not replace ordinary communication. It works with it. It shows that quantum information has rules different from classical information, but it does not overthrow the causal structure of the universe. It is a partnership between the strange and the familiar. Entanglement supplies the deep correlation. Measurement consumes the original state and produces a random outcome. Classical communication carries the outcome to Bob. Bob's local operation completes the transfer. Each part is necessary. Remove one, and the magic, if we may use that word very carefully and with a lab coat nearby, disappears. There is also a delicate lesson here about what it means to know something. Alice never learns the full state she is teleporting. The state passes through the procedure without becoming an ordinary message. It is not translated into a complete classical description. This is unlike sending a photograph where the image is converted into bits, transmitted and reconstructed. An unknown quantum state cannot be fully converted into classical data from a single copy. Teleportation avoids that impossible step by using entanglement as part of the transfer. The state is carried through a relational process rather than copied into a list of instructions. This is why teleportation feels almost like a loophole in the rules, though it is not. Nature forbids copying unknown quantum states. It forbids faster than light messaging. It makes measurement disturb what is measured. And then, within those same rules, it permits teleportation. Not by breaking the restrictions, but by satisfying all of them at once. The original is destroyed, so no cloning occurs. A classical message is required, so relativity is safe. Alice never fully learns the unknown state, so measurement limits are respected. Bob ends with the state, so the transfer succeeds. It is a very quantum kind of cleverness. Not a cheat, but a lawful surprise. In future quantum networks, teleportation could become a basic method for moving quantum information between nodes. A quantum internet, if fully developed, would not simply be a faster version of the current internet with more impressive branding. It would connect quantum devices using entanglement and allow tasks that depend on quantum states being shared, transferred, or protected. Teleportation could help link quantum processors, extend secure communication, and move fragile quantum information without directly sending the original physical carrier through a noisy channel. Instead of forcing a delicate state to survive the whole journey, one can use entanglement and classical signals to recreate the state at the destination. This is why scientists care so deeply about building reliable entanglement over distance. The entangled pair is the channel, but not in the ordinary sense of a wire carrying a message. It is a prepared shared resource that makes the later transfer possible. Establishing entanglement across long distances is difficult because losses and decoherence interfere. Photons may be absorbed in fibers. Atmospheric conditions may disrupt free space links. Quantum memories, devices that can store quantum states long enough to be useful, are hard to build. Repeaters for quantum networks must handle entanglement without simply copying quantum information, because copying is forbidden. The whole engineering challenge is shaped by the strange rules we have been discussing. It is not merely building smaller electronics, it is learning to build with entanglement itself. There is something almost poetic in the fact that teleportation depends on both destruction and reconstruction. But we promised not to drift into poetry, so let us put it more plainly. The original state at Alice's side is lost in the measurement. Bob's system becomes the new carrier after he applies the needed correction. The information has not been duplicated, it has been transferred. That is the sober heart of the matter. The old state is not here anymore, the new state is there, The process obeys every known rule, while still sounding like it should have been invented by someone writing science fiction in very comfortable socks. One of the most helpful ways to think about it is to imagine a delicate pattern that cannot be photographed, cannot be copied, and cannot be described completely in words. Alice has the pattern on one fragile surface. Bob has a blank surface far away. But Alice and Bob also share a strange pair of linked tools prepared in advance. Alice uses her tool together with the original pattern, and that use destroys the original while producing a small, ordinary instruction for Bob. She sends the instruction. Bob uses his link tool and the instruction to make his blank surface take on the pattern. The pattern was never sent as a photograph. The original was not preserved. The instruction alone was not enough. The shared tools alone were not enough. Only the combination worked. As always, the analogy has its limits. Quantum states are not patterns painted on surfaces, and entanglement is not a pair of tools in a drawer. But the image captures the structure. Teleportation is not a transportation service for objects. It is a protocol for transferring quantum information using an entangled resource and classical communication. It moves what is physically meaningful about the state, not the material carrier itself. This brings us back to the deeper meaning of entanglement. It is not only that entangled particles behave strangely when measured, it is that their shared state can perform tasks no classical shared randomness can perform. Entanglement changes what is possible with information. It lets quantum systems coordinate, transfer, protect, and process states in ways that do not fit the older picture of separate objects carrying separate facts. The impossible becomes possible, but only in the exact way quantum rules permit. The universe remains strict. It is just strict according to a rulebook much stranger than the one we first imagined. So when we hear quantum teleportation, we should let go of the glowing chamber for now. No person disappears. No object dissolves into light. No signal outruns a beam of light. What happens is quieter and more exact. A fragile quantum state is transferred from one system to another. Entanglement provides the shared structure. Measurement consumes the original. Classical communication carries the necessary instruction. Bob's system becomes what Alice's system was, not by copying it, not by flying it across space, but by completing a carefully arranged quantum exchange. And once that idea settles, entanglement begins to look less like a single odd phenomenon, and more like a language the universe uses to organize information. It appears in laboratories as a resource. It appears in communication as a security tool. It appears in computation as a source of power. And when physicists look toward the deepest questions, toward black holes, horizons, space-time, and the structure of reality itself, entanglement appears there too, not as a small curiosity at the edge of theory, but as something that may help explain why space has shape, why information is never easily lost, and why the universe may be stitched together in ways far more subtle than distance alone can describe. When entanglement first appears in a laboratory, it can feel like a small and delicate thing, a pair of photons, a carefully shielded device. A detector clicking softly in a room full of equipment that would prefer not to be touched by dust, heat, elbows, or anyone carrying coffee too confidently. But the more physicists studied entanglement, the less it seemed like a small curiosity. It began to appear not just as an odd trick of particles, but as a deep clue about how reality itself may be arranged. And nowhere does that clue become more dramatic, more difficult, and more quietly enormous than at the edge of a black hole. Black holes already ask a great deal of the imagination. They are regions of space where gravity is so strong that, once something crosses the boundary known as the event horizon, it cannot escape back to the outside universe. Not light, not matter, not a brave little message saying, "Actually, I have reconsidered." The event horizon is not a physical surface like the skin of a balloon or the wall of a cave. You would not necessarily feel a bump as you crossed it, assuming the black hole was large enough and you were having an exceptionally unfortunate day. It is a boundary in space-time, a line of no return, defined by what can and cannot reach the outside world. For a long time, black holes were treated as objects that swallowed information. Drop a book into a black hole, and the outside universe loses access to the book. Drop a clock, a teacup, a piano, or a very determined encyclopedia, and all the details seem to vanish behind the horizon. From the outside, the black hole can be described by only a few broad properties, such as its mass, its spin, and its electric charge. That is a strangely simple description for something formed from complicated matter. A black hole made from collapsing stars and a black hole made from an enormous pile of old receipts could, in principle, look the same from outside if those broad properties matched. One suspects the receipts would still feel morally responsible, but physics would not keep their itemized history on display. This simplicity troubled physicists because quantum theory is deeply connected to information. In ordinary quantum mechanics, information about a system is not supposed to be destroyed. It may become scrambled, hidden, spread out, or nearly impossible to reconstruct, like a tidy desk after a busy week, but the underlying rules preserve it. If you could track every particle and every interaction perfectly, the past would not be simply erased. But black holes seem to threaten that principle. If information falls behind the horizon, and the black hole eventually disappears, where does the information go? That last part comes from Stephen Hawking. In the 1970s, Hawking showed that black holes are not completely black when quantum effects are considered. They can emit a faint thermal radiation and slowly lose energy. Over immense timescales, a black hole can evaporate. For large black holes, the radiation is incredibly weak, far colder and quieter than anything one could warm a biscuit by. But the idea is profound. A black hole is not an internal prison. It can shrink away. Here is the problem. Hawking radiation appeared to be thermal, meaning it seemed to carry no detailed information about what formed the black hole. If the black hole swallows a library and then evaporates into featureless radiation, what happened to the words in the books? Not the paper and ink in the ordinary sense, but the quantum information describing the exact state of everything that fell in. Did it vanish? If so, quantum theory would be in serious trouble. If not, how does it escape? This became known as the black hole information paradox, one of the great puzzles in modern physics. It is the sort of problem that begins with a simple question and then quietly removes the flaw beneath several major theories. Entanglement sits right at the centre of the puzzle. Hawking radiation is often described as arising from quantum fields near the horizon. Very loosely, pairs of quantum excitations can be treated as connected across the boundary. One part escapes outward as radiation, while the other is associated with the black hole. This picture is simplified, but it helps capture why entanglement matters. The escaping radiation is not independent of what remains behind. It is entangled with the black hole. As the black hole radiates, more and more of the outside radiation becomes entangled with the interior, or with whatever degrees of freedom describe the black hole. That phrase, degrees of freedom, simply means the hidden ways a physical system can store information. Not knobs and switches you can see, but the possible internal arrangements that make one state different from another. At first, this entanglement seems manageable. Radiation leaves, and it is entangled with what remains. But if the black hole continues to evaporate, a strange tension grows. If the information is to survive, then the late radiation should somehow carry correlations with the early radiation, so that the complete pattern of outgoing radiation contains the information that fell in. But according to the original Hawking calculation, each new bit of radiation seems entangled with the black hole interior instead. Quantum theory has strict rules about how entanglement can be shared. A system cannot be fully entangled with two independent partners in the same way at once. It is not like a group chat where everyone can be equally confused together. Entanglement has limits, and those limits create pressure. This pressure led to some of the sharpest debates in theoretical physics. If information escapes in the radiation, then the radiation cannot be completely featureless. If the horizon is smooth, as general relativity suggests for a large black hole, then the near-horizon physics should behave in a certain quiet way. If quantum information is preserved, then subtle correlations must eventually appear in the outgoing radiation. Trying to satisfy all of these ideas at once is like trying to tuck a fitted sheet neatly around a mattress, while the mattress is reciting philosophy and slowly evaporating. One proposed resolution is that the information is not lost, but encoded in extremely subtle correlations within the Hawking radiation. Early on, the radiation may look nearly thermal, nearly random, but as more radiation escapes, the pattern begins to carry information about the black hole's original state. The information is not printed plainly on each particle, any more than an entangled pair carries a readable message on one side alone. It is hidden in correlations across the entire radiation field. To recover it would require an almost impossible level of measurement and computation, but impossible in practice is not the same as impossible in principle. A diary shredded into dust and scattered across a continent still has a history, though no one is likely to reconstruct your thoughts about breakfast. This idea makes entanglement not just a side detail, but a kind of accounting system for what a black hole knows. As the black hole evaporates, the pattern of entanglement must change if information is preserved. The radiation cannot remain simply entangled with an interior that eventually disappears. Somehow, the entanglement structure must shift so that the outside radiation carries the story. This is one reason black holes have become central to the study of quantum information. They force physics to ask what information is, where it lives, and how it can be scrambled without being destroyed. Scrambling is an important word here. A black hole appears to be an extraordinary scrambler of information. When something falls in, its information is not neatly stored like a file in a cabinet. It becomes mixed among the black hole's microscopic degrees of freedom in an incredibly complex way. Think of stirring a tiny drop of milk into tea. At first, you can see the swirl. Soon the milk is spread throughout the cup. The information about where the milk began has not vanished from the laws of physics, but it has become distributed through the motion of countless molecules. Now imagine a black hole doing something similar, but with quantum information, gravity, horizons, and a level of complexity that makes the tea look like a children's puzzle with 3 pieces and one of them already in place. Entanglement is the language physicists use to describe this distribution. It tells us how parts of a system share information, how much can be known locally, and how much is stored in relations. In black holes, this becomes especially strange because space itself is involved. The horizon divides the outside from the inside. Quantum fields can be entangled across that boundary. The interior may not be accessible, yet its relationship with the exterior matters. This makes the black hole not just an object in space, but a challenge to our idea of separateness. What counts as inside? What counts as outside? If information is stored in correlations, can a boundary truly hide it forever? These questions connect to another remarkable idea, the holographic principle. The name may sound as if the universe is a shiny sticker on the back of a notebook, but the idea is serious. It suggests that the information contained in a region of space may be describable by information on its boundary. This thought grew partly from black hole physics. The entropy of a black hole, which is a measure related to the number of ways its microscopic state can be arranged, is linked not to the volume inside the black hole, but to the area of its horizon. That was deeply surprising. Ordinary objects usually store more information when they have more volume. A larger cupboard can hold more things than a smaller one, unless both are managed by someone with an unusual talent for folding. But black holes seemed to say that the boundary area was what mattered. From this came the broader suspicion that space-time itself may have a holographic character. Perhaps the physics inside a region can be encoded on its boundary in a lower dimensional description. This is not saying the universe is fake, or that your chair is merely a projection in the cheap science fiction sense. Your chair remains very capable of supporting you, and your shin remains very capable of discovering the coffee table in the dark. The holographic principle is about how information may be organized at a deep level. It suggests that what looks like a volume of space could be described by information living on a boundary. Entanglement appears again because the way that information is connected may help give rise to the geometry we experience. This leads to one of the most fascinating modern ideas, that space-time itself may emerge from entanglement. In ordinary thinking, space is the stage on which entanglement happens. Two particles are here and there, and entanglement connects their quantum states across the distance. But some theories suggest the relationship may go the other way around. The pattern of entanglement may help build the sense of space. Systems that are strongly entangled may be, in some deep description, close together. Systems with less entanglement may be farther apart. Distance, in this view, is not the most basic ingredient. It is a result of how information is connected. That's a very large idea, and it should be approached with care. It does not mean moving your favourite armchair closer to the biscuit tin by thinking affectionate thoughts about it. Entanglement in quantum gravity is not a household organising tool, which is a shame but probably for the best. The idea is that, at the deepest level, the smooth geometry of space may arise from networks of quantum entanglement. What we experience as distance and shape could be a large-scale description of underlying informational relationships. Like temperature emerging from the motion of molecules, space might emerge from patterns of quantum connection. There is a famous proposal linking entanglement with wormholes, the hypothetical tunnels through space-time often imagined as shortcuts between distant places. In this idea, certain kinds of entangled systems may be mathematically related to certain kinds of wormhole geometry. This does not mean that every entangled pair has a little tunnel inside it that one could crawl through with a packed lunch. The wormholes involved are not practical travel routes. They are theoretical structures, often not traversable, meaning nothing can simply pass through them as in a science fiction film. But the connection suggests that entanglement and geometry may be two ways of describing related physics. A quantum relationship and a space-time bridge may, in some cases, be different faces of the same deeper structure. This is why entanglement has become so central in attempts to understand quantum gravity. General relativity describes space-time as smooth and dynamic. Quantum mechanics describes matter and information through states, probabilities, and entanglement. To combine them, physicists may need to understand how geometry and quantum information fit together. Black holes are the testing ground because they are both gravitational and quantum. They curve space-time so strongly that relativity is essential, and they involve radiation, entropy, and information in ways that demand quantum theory. They are not just cosmic drains. They are laboratories built by nature, though admittedly not laboratories one can visit safely or claim expenses for. The idea that space-time might emerge from entanglement also changes how we think about empty space. In quantum field theory, even the vacuum is not simply nothing. It has structure. It contains fluctuations and entanglement between different regions. What we call empty space is more like a quiet sea with hidden patterns than a blank absence. Nearby regions of a field are naturally entangled. This local entanglement may be part of what gives space its smoothness. If you tried to remove all entanglement from the vacuum in a region, the geometry itself might no longer behave normally. This suggests that entanglement is not merely sprinkled on top of space like sugar on porridge. It may be part of the recipe. Again, we should be careful not to overstate what is known. These are active areas of theoretical physics. Not every idea is settled. Not every proposal has direct experimental confirmation. The connection between entanglement, black holes, and space-time is one of the most exciting and difficult frontiers in modern science, which means it contains both deep insight and many unanswered questions. Physicists are still debating how information escapes black holes, what the interior of a black hole means in a complete quantum theory, and whether space-time truly emerges from entanglement, or whether entanglement is simply one important clue among several. The honest answer is that we do not yet have the full theory. The universe has not handed over the instruction manual, and if it has, it has written it in very small print near the event horizon. But what has become increasingly clear is that entanglement is not optional background decoration. It is woven into the problems themselves. The black hole information paradox is an entanglement problem. The holographic principle is deeply tied to how information and correlations are arranged. The emergence of space-time, if that idea is correct, may depend on entanglement patterns. Even the smoothness of ordinary space may be connected to the entanglement structure of quantum fields. The same phenomenon that begins with two small particles in a laboratory now appears at the edge of the biggest questions physics can ask. There is something humbling about that. A pair of photons measured on opposite sides of a room, and a black hole swallowing starlight may seem to belong to completely different scales of reality. One is delicate and small, the other is vast and gravitationally overwhelming. Yet both point toward the same lesson. Information is not always stored locally in the way common sense expects. Relationships can be physically fundamental. The whole can contain facts that are not found in the parts alone. Whether in a laboratory detector or near a horizon from which light cannot return, entanglement keeps reminding us that separateness is not as simple as it looks. It also changes the emotional shape of black holes. They are often presented as destroyers, cosmic monsters that devour everything nearby. And yes, from a practical point of view, one should not place a black hole on a list of relaxing holiday destinations. But in modern physics, black holes are also teachers. They reveal tensions between our best theories. They force questions about information, entropy, time, and quantum states. They take ideas that seem small and abstract and stretch them across the structure of the cosmos. A black hole is not merely a place where things disappear. It is a place where the rules of reality become impossible to ignore. So when entanglement appears in black hole physics, it is not simply because physicists enjoy making difficult things even more difficult, though one might occasionally wonder. It appears because the problem demands it. If radiation is entangled with the black hole, if information must be preserved, if horizons divide space but quantum states refuse to be neatly divided, then entanglement is the natural language. It tells us where information may be hiding, how it may be shared, and why the old picture of isolated regions of space may not be enough. This brings us to a quieter but deeper possibility. Maybe entanglement is not just something that happens inside reality. Maybe it helps define what reality is. Maybe the reason space has shape, the reason regions are connected, the reason information can be scrambled but not lost, all depend on quantum relationships beneath the level of ordinary objects. This does not make the world less real. If anything, it makes reality more structured than it first appeared. The familiar world of tables, lamps, planets, and sleepy observers may be the large-scale surface of a deeper informational order. And now, after particles, hidden variables, experiments, no signalling, teleportation, and black holes, the question begins to return in a more complete form. We started with two particles that seemed mysteriously linked. We found that the link could not be explained by ordinary hidden cards. We saw that it could not send messages faster than light. We saw that it could move quantum states without moving objects, and now we see it reaching into the foundations of space-time itself. Entanglement is no longer just a strange connection between distant things. It may be one of the main clues to why things can be distant at all, why information has structure, and why the universe holds together as a single physical story rather than a collection of separate facts drifting in the dark. So, after all this wandering through particles, hidden cards, careful experiments, no signalling, teleportation, black holes, and the possible stitching of space itself, we can return to the question that brought us here in the first place. What is entanglement, really? The most careful answer is also the simplest to say, though not always the easiest to feel. Entanglement is a shared quantum state between systems, where the whole cannot be fully described by describing the parts separately. It is not just that two particles know about each other. It is not just that their outcomes match. It is not a secret message, not a hidden wire, not a tiny invisible rope stretched across the universe. It is a physical relationship in which the best description belongs to the combined system, not to each piece on its own. That may sound almost too calm for something that has caused nearly a century of argument, experiment, confusion, and occasional philosophical indigestion. But that is often how deep ideas are. They do not always look dramatic once stated plainly. Gravity is the curvature of space-time, which sounds neat enough until you realise it means the floor is pushing you through geometry. Evolution is descent with modification, which sounds tidy until you remember it built orchids, whales, fungi, and people who argue about parking. Entanglement is a shared quantum state, and inside that quiet phrase is an entire reshaping of what separateness means. In the everyday world, we usually assume that the parts come first. A house is made of bricks, beams, pipes, wires, doors, windows, and one cupboard that somehow becomes the permanent home of things nobody can identify. A sentence is made of words. A meal is made of ingredients. A clock is made of gears, springs, circuits, or vibrating atoms, depending on how serious the clock is feeling. We understand the whole by looking at the pieces. This habit works beautifully for many things. It is one of the reasons human beings can build bridges, repair bicycles, bake bread, and occasionally assemble flat-pack furniture without weeping openly. Quantum entanglement tells us that this habit is not always enough. Sometimes the whole contains information that is not stored in the parts separately. If two particles are entangled, the state of the pair may be definite in a way that neither individual particle is. Measure one, and the result may be random. Measure the other, and that result may be random too. But compare the records, and the pattern appears. The information was not sitting plainly in either particle, it belonged to the relationship. This is why ordinary analogies help for a while and then quietly abandon us near the edge of the road. Two gloves in two boxes are correlated. Open one box and find a left glove, and you know the other box contains the right glove. But the gloves had their handedness all along. Two shuffled cards can be correlated. Two clocks can be synchronized. Two friends can agree on a plan before separating. All of these are ordinary relationships based on hidden details, shared preparation, or predictable mechanisms. Entanglement is different because Bell tests show that entangled particles cannot be explained as if they simply carried a complete set of local hidden answers from the start. That result matters because it removes the most comfortable explanation. It would be comforting to say the particles are like envelopes carrying sealed instructions. It would be comforting to say quantum mechanics merely hides details we do not yet know. It would be comforting to say the universe is classical underneath, and quantum uncertainty is only our ignorance wearing a complicated hat. But the experiments do not let us keep that comfort in its ordinary form. The correlations are too strong, too carefully arranged, too far beyond what local hidden cards can produce, and yet entanglement does not allow chaos. This is just as important. It does not let us send messages faster than light. It does not let Alice control Bob's detector from across the galaxy. It does not let anyone build an instant communication device, which is unfortunate for science fiction, customer service, and anyone trying to ask whether there is milk in the fridge from another continent. Each local outcome remains random. Alice cannot choose what result she gets. Bob cannot look at his own list and know what Alice did. The strange order appears only when the records are later compared through ordinary communication. So entanglement is not communication. It is correlation without a classical cause that fits our old expectations. It is a shared structure that produces patterns stronger than any local prearranged explanation, while still obeying the rule that usable information cannot outrun light. That combination is the source of much of the mystery. Entanglement is bold enough to challenge separability, but disciplined enough to preserve causality. It is not a rebellion against physics. It is physics revealing that its deeper rules were stranger than the surface ones. If we ask what is actually happening when a measurement is made, the answer depends partly on interpretation. Some physicists say the quantum state collapses when measured. Some say all possible outcomes occur in branching worlds. Some say there are deeper variables guiding particles in a non-local way. Some say the safest thing is to speak only of experimental outcomes and the probabilities connecting them. These interpretations differ in language and picture, but the measurable fact remains. Entangled systems produce correlations that quantum theory predicts and experiments confirm. Whatever picture we prefer, the universe keeps returning the same results. This is a useful place to be humble. Physics does not always give us an image that fits comfortably in the mind. Sometimes it gives us rules that work, experiments that confirm them, and interpretations that remain debated. That does not make the science weak, it makes the subject deep. We can know very precisely how entanglement behaves without having a single everyday picture of what it is doing behind the scenes. We know how to create it, test it, lose it, use it, and protect it. We know it is fragile in ordinary environments and powerful in carefully controlled systems. We know it is central to quantum information. We know it is not a message. We know it is not ordinary ignorance. We know it is real because it changes what can be measured and what can be done. Perhaps the most grounded way to think of entanglement is as a form of physical togetherness that does not require closeness in space. That sentence needs care. It does not mean the particles are emotionally attached. It does not mean they are connected by a force. It does not mean distance disappears. It means that, in the quantum description, the state of the pair remains one thing, even when the particles are separated. Their locations may be far apart, but the information needed to describe their joint behavior is not divided into two independent local packages. The relationship has physical content. This idea can feel less strange if we remember that physics has taught us many times not to confuse our first impressions with reality. The solid table is mostly empty space structured by fields and forces. The colour of an object is not a property floating alone, but a relationship between light, matter, and eyes. Time feels universal until relativity shows that motion and gravity change its pace. Heat feels like a substance until we learn it is connected to microscopic motion. The everyday world is real, but it is not transparent. It gives us useful summaries, not the final machinery underneath. Entanglement is another reminder that the deeper description may not resemble the furniture of common sense. And still, common sense is not useless. It simply has a domain. It works for cups, shoes, buses, biscuits, and the practical question of whether you have turned the oven off. It works because large objects interact constantly with their environments. Decoherence hides delicate quantum relationships from ordinary view. The world around us looks classical because its quantum possibilities become entangled with air, light, heat, and countless surrounding degrees of freedom so quickly and thoroughly that the clean quantum behavior becomes effectively inaccessible. That is why you do not see your teacup in a delicate superposition of being on the table and under the sofa, unless you live with a cat, in which case the situation may require a separate investigation. Entanglement is therefore both everywhere in principle and difficult to preserve in practice. Quantum systems interact, and interaction can create entanglement, but uncontrolled interaction with the environment spreads and scrambles it. Laboratory entanglement requires isolation, precision, and care. The systems must be protected from noise. The measurements must be well chosen. The data must be compared properly. The whole business is less like summoning a mystery, and more like keeping a very delicate candle alight in a house full of drafts. What makes entanglement especially important today is that it is no longer only a puzzle, it is a resource. In quantum computing, entanglement helps create forms of information processing that classical systems cannot easily reproduce. In quantum communication, it can help detect eavesdropping and support new security methods. In quantum teleportation, it allows an unknown quantum state to be transferred from one system to another, not by moving matter and not by copying the state, but by using a shared entangled pair, a joint measurement, and ordinary classical communication. In each case, Entanglement is not just something to marvel at. It is something that can be used. That transformation is remarkable. Einstein worried that entanglement showed quantum mechanics was incomplete. Bell showed that the worry could be tested. Experiments showed that nature violates the limits of local hidden instruction theories. Later generations learned to treat entanglement as a tool. The thing that once seemed like an embarrassment became one of the foundations of a new technology. Physics has a habit of doing this. Yesterday's philosophical headache becomes tomorrow's engineering challenge, and eventually someone has to write a manual for it. The deeper possibility is that entanglement may be more than a tool inside space-time. It may help explain space-time. This remains a frontier, not a settled bedtime fact to tuck neatly under the pillow. But the hints are strong enough to be taken seriously. Black holes connect gravity, entropy, information, and quantum mechanics in ways that keep pointing back to entanglement. The holographic principle suggests that information in a region may be related to its boundary. Some approaches to quantum gravity suggest that the geometry of space may emerge from patterns of entanglement. Nearby regions may be nearby not because distance is fundamental, but because the underlying quantum information is connected in a particular way. That idea is still being explored, but it changes the scale of the question. Entanglement might not be merely a weird connection across space. It might be part of what makes space possible. If that is true, then asking how entangled particles remain connected across distance may be partly backwards. Distance itself may be a higher-level feature that emerges from deeper quantum relationships. The road may be made from the connections rather than the connections lying across the road. That is a large thought, and not one to force too quickly into a simple image. Still, it suggests why so many physicists now treat entanglement as central rather than decorative. So, what is entanglement really? It is the refusal of certain quantum systems to be fully understood as separate things. It is the presence of information in relationships rather than in individual parts alone. It is the source of correlations that defeat local hidden cards but cannot be turned into faster-than-light messages. It is a fragile state in the laboratory, a practical resource in quantum technology, and perhaps a clue to the deep structure of space-time. It is not magic. It is not a metaphor. It is not a mood. It is a tested feature of the physical world, and the fact that it sounds impossible is mostly a comment on the limits of human intuition. There is something reassuring in that, oddly enough. The universe does not owe us simplicity, but it does offer consistency. Entanglement is strange, but it is not random nonsense. It follows rules. It can be predicted. It can be measured. It can be used. It refuses to fit into old pictures, yet it does not dissolve into anything goes. Science is at its best in this middle place, where wonder is held steady by evidence, and mystery does not mean confusion, but an invitation to look more carefully. By now, the quiet room around you may feel much the same as when we began. The walls are still there, the blanket is still warm, the night outside, if it is night where you are, has not turned visibly quantum. The world has not become less solid because we have looked beneath it, but perhaps it has become a little less ordinary. The objects around you are made of matter whose deepest rules are not the rules of ordinary objects. The light reaching your eyes is made of quantum fields. The atoms in your body obey principles that would have sounded absurd before experiments forced us to take them seriously. Beneath the calm surface of things, nature is not a clockwork machine, made only of separate parts. It is a web of possible states, measurements, fields, interactions, and sometimes shared descriptions that stretch our idea of what a thing can be. And if that sounds large, it is. But it is also very precise. Entanglement does not ask us to abandon reason. It asks us to refine it. It asks us to stop demanding that particles behave like tiny versions of familiar objects. It asks us to accept that the whole may be physically richer than the parts, that relationships may carry information, and that separateness in space is not always separateness in state. These are not loose philosophical gestures. They are lessons extracted from experiments, from detectors clicking in dark rooms, from correlations counted and checked, from predictions tested again and again. There is a quiet human lesson here too, though we should not overdo it. Particles are not people. Quantum states are not emotions. Entanglement is not a scientific proof that everyone is spiritually linked, or that thinking warmly about the kettle will make it boil faster, though one may certainly try if the evening is slow. But there is still something meaningful in discovering that relationship can be fundamental in physics, not in the sentimental sense, but in the structural sense. The universe is not always best understood by isolating every piece and ignoring the connections. Sometimes the connection is the thing you must understand first. That idea has carried us from the smallest experiments to the edge of black holes. It began with pairs of particles and led to questions about information, causality, and the shape of space. It challenged Einstein, inspired Bell, drove generations of experiments, and now sits at the center of quantum technologies and quantum gravity research. Not bad for something that cannot be seen directly, cannot be used to send an instant message, and sounds at first like a word for tangled headphones. And so, dear listener, we come gently back to where we started. Wherever you are, whatever time it is in your corner of the world, you are sitting inside a universe whose deepest rules are more subtle than ordinary experience reveals. Things can be separate and yet described together. Outcomes can be random alone and ordered in relation. Information can belong not to one place or another, but to the pattern between them. Entanglement is the name we give to that strange quantum togetherness, precise enough for experiments, powerful enough for technology, and deep enough to make reality feel just a little wider than before. If this journey has brought you some calm, some curiosity, or perhaps just a softer place to rest your thoughts, I would be ever so grateful if you liked the video, subscribed, or shared this quiet corner of science with someone who enjoys wondering about the universe at a gentle pace. And I would still love to know where you're listening from tonight. If you could send one entangled particle anywhere, where would it go? Across the room, across the planet, or far out beyond the stars, paired with its distant partner, in a way that does not send a message, does not pull a thread, and yet still refuses to be described alone. For now, there is no need to solve the universe before sleep. The particles can keep their strange correlations. The black holes can keep their difficult secrets. The physicists can keep arguing carefully and productively over what it all means. You can simply rest with the thought that reality is deeper than it first appears, and that even in the smallest parts of nature, connection can be real without being visible, powerful without being loud, and mysterious without being beyond understanding. Sleep well, fellow traveller, wherever you are, and whatever quiet state the night has found you in.